Hi everyone, welcome to goclasses. In this lecture, we will study average memory access time AMAT. Let's study this topic. And this is a very important topic from the gate exam point of view. There are many questions based on this topic. Before we study average memory access time concept, all the concepts, let me discuss some major misconceptions that students have related to average memory access time. Related to this concept, there are some major misconceptions that many students have. So let me discuss them. The misconception of simultaneous access or parallel access, this terminology, this is a misconception. Also, misconception related to look aside cache. So let's discuss these two misconceptions. What is this misconception? See, if you did not study computer organization, or if you did not study cache memory so far from anywhere, then you don't have to worry, because in this lecture we will study the correct concepts, we will solve the gate pyqs. But if you are a repeater, if you have already studied this computer organization subject or cache memory from some non-standard resources, from some other coaching, then you may have these misconceptions. There is a high possibility that you may have these major misconceptions. So let me discuss these two words: parallel access, simultaneous access. These two words you may have seen. Yes or no? This terminology you may have seen. You may have solved some gate pyqs also using this simultaneous access. And in some gate pyq, in some questions, definitely you may have been confused. You may have scratched your head thinking which to assume in this gate pyq. Should I assume simultaneous access? Should I assume hierarchical access? So this type of confusion also you may have had. Okay. So let me tell you that there is no confusion in any gate pyq. There is no confusion. The reason is very simple, because this simultaneous access or this parallel access, this is not a standard terminology. First of all, if you follow any standard book of the computer organization subject, any standard resource, if you follow, then you will never find these concepts: simultaneous access, parallel access. These concepts you will never find in any standard resource. These are, I can say, self-made concepts by some people. But let me tell you that this simultaneous access or parallel access, this is not a standard terminology. Look ahead cache, this is a standard terminology. Okay, I will come back to that. So you can see no standard resource, books, university notes, nptl mention any such terminology. This terminology, simultaneous access or parallel access. Also, there is no gate exam question which is based on such imaginary self-made terminology, that is simultaneous access or parallel access. There is no gate exam question based on this type of concept, this type of terminology. Also, we will not use this terminology, this simultaneous access or parallel access. This terminology we will not use in our lecture, because we will follow the standard books, we will follow the standard resources as always. And in the standard resources, you can see there is no standard resource which mentions this terminology, simultaneous access or parallel access. So we will also not use this terminology. Okay, very simple. So from today onwards, you also should not use this type of terminology, simultaneous access or parallel access, because this is not a standard terminology. This is not given in any standard resource, books, university articles, university slides, notes, nptl, anywhere. Okay, now let me discuss some misconceptions related to look aside cache. See, look aside cache, this itself is not a misconception. This is a standard terminology. But let me tell you, this is covered, this is given, this look aside cache, this design, or I can say this concept is covered, or it is given in very few university slides or university notes. So you can see very few, or I can say some university slides or notes, they talk about a design, a model, look aside caches. At the end of this lecture, I will discuss what is look aside cache. But right now, some misconceptions I want to talk briefly. Okay, so you can see, remember, this is a standard terminology because it is covered in some university slides, or I can say that it is a concept. But let me tell you, this concept is not used in the modern processors. Okay, at the end of this lecture also, I will discuss look aside cache. Okay, there also I will tell you the reason. What are the reason why this is not used in the modern processors? that also I will discuss. But let me tell you that this look aside cache, even though this is a standard terminology, this is a standard concept, but it is not used in the modern processors. Also, if you study the standard books of computer organization, all the widely followed standard books, for example, Hennessy and Peterson, this is widely followed. This is most followed standard book of computer organization subject. Also, Morris Mano, William Stellings, Carl Hamacher. So you can see, if you follow these books, if you study these books, then none of them, none of them mention or none of them cover the look aside concept. Okay. So you can see all these standard books that are followed by the IIT professors. If you study from NPTL, if you go to IIT, IISc Bangalore, in any top college, then these professors who create the gate exam question, they follow these books for the computer organization. Hennessy and Peterson, this is the most followed book. But other books like Carl Hamacher, William Stellings, Morris Mano, these books are also widely followed. And in these books, none of them cover the concept of look aside cache. None of them will mention the concept of look aside cache. The reason is very simple, because it is not used in the modern processors. Okay. So this look aside cache, this is basically, you can say, in the modern processors, this is non-existent, or I can say that this is more of a theoretical or historical model. Okay. In the old times, when there were single processing computers, nowadays our computers are multitasking, our processors, our computers are, we have operating system, so our computers are multi-programming, multitasking. But in the old days, when our computers, when our processors were single tasking, or I can say single processing, at that time, this look aside cache, this design was used in some computers. Okay. In the old times, or in some embedded systems, in some specialized systems, this was used. But this is rarely, or I can say this is not used in the modern processors. Also, let me tell you that no gate exam question is based on the look aside model of caches. The reason is very simple, because to create the gate exam question, the IIT professors, they follow these books: Hennessy, Peterson, Morris Mano, Stallings, Carl Hamacher. These books they follow. And in these books, this look aside design of the caches, this is not given, this is not covered. Okay. So there is no gate exam question. In this session, we will solve all the gate PYQ based on average memory access time. And you will see this, that there is no gate exam question that is based on look aside model of caches. Okay. So let me tell you a note that first, in this lecture, first we will study the correct concepts. Then we will solve all the gate PYQs. Then we will also solve top university questions from Berkeley, MIT, Stanford, and many top university questions also we will solve. And at the end, you can see, at the end, I will discuss look aside cache in detail. It is optional, because remember, there is no gate exam question which is based on it. And also this concept, look aside caches, this concept is no longer used in the processors, in the modern processors. But we can discuss it, and then we can forget about it, because it is not useful for the gate exam. There is no gate PYQ based on it. Okay. So you can see, at the end we will discuss it, and you can forget it after the discussion. Okay. Very simple. I hope you understood. So let me discuss what are the sources I have used in this lecture. So all the concepts that I will teach in this lecture, and all the screenshots that I have put in this lecture, these are taken from these books, or I can say from these resources: Hennessy and Peterson. This is the most widely followed book for computer organization subject. Also, IIT Delhi computer organization book by Professor Samruti Sarangi. Also, William Stellings, Carl Hamacher 6th edition, MIT Slides and Exams, Princeton University Slides, and Georgia Tech. So these are the resources I have followed, I am going to follow in this lecture. So all the screenshots that you will see, these are taken from one of these resources. Okay. So now let's start. Our first topic is memory hierarchy. Let's study what is memory hierarchy. How do we usually visualize the memory in computer systems? If you ask anyone who has not studied cache memory or computer organization subject, if you ask them how do they visualize the memory in the computer system, then what they will tell you? They will tell you that there is a hardware component in our computer. Okay. And this hardware component has many cells, or I can say many locations, maybe millions of locations are there. Okay, every location has an address. Using that address, we can access that location to read or to write. So this type of visualization we have for memory in the computer system, right? Yes or no? This is how we usually visualize the memory in the computer system. But let me tell you, in the computer system, actually the memory is in levels. We have main memory, that is fine. Okay, main memory is same. I can say the visualization of main memory will be same. But actually the overall, the complete memory, if you see in the computer system, then that will have levels. There will be cache memory, there will be main memory, there will be hard drive, hard disk. Okay, so basically the memory in the computer system, that is divided into levels, or I can say there is a hierarchy. Okay, there is a hierarchy of memory, I can say. So let's see that in this chapter we are going to study that the memory in the computer system, that is basically built hierarchically in different levels or in different layers. Okay, so you can see memory in the computer system, in the modern computer systems, the memory is actually built hierarchically. There are different levels of memory. You can see the CPU has registers. If the data is in the register, then CPU can access the register very quickly. Okay, after this register, you can see the next level is cache memory. And then after this cache memory, the next level is main memory. And after the main memory, the next level is disk. So you can see that in our computer systems, in the modern computer systems, the memory is actually built hierarchically. Okay, and you can see when you go from registers to disk, basically as you go far, okay, from the CPU, as you go far, then you will see that the memory becomes slow. Okay, registers are very fast. Cache memory is also faster than main memory. Main memory is faster than disk. So you can see when you go far away from CPU, then you will see that memory will become slow, but memory will become huge. You can see hard drive is huge. In our computers we have terabyte of hard drive, yes or no, hard disk. But the main memory will be around, I can say, maybe 16 GB, right? Yes or no, 8 GB. So that kind of main memory we have. And the cache memory will be even smaller. So I can say that when you go far away from CPU, as you go far, then you will see that the size of memory will increase, and also the memory will become slower, and the memory will become cheaper. Okay, you can see slow and cheap. The hard drive that is slow also, that is cheap also. You can purchase terabytes of memory. Basically the hard drive you can purchase maybe 4,000, maybe 3,000 rupees. Okay, so you can see that main memory is actually more expensive than disk, and cache memory is much more expensive than main memory. So like that. Okay, so you can see in the computer systems the memory is built hierarchically. You can see there are levels. There is a hierarchy here. Okay, now let me tell you that before this cache memory lecture, we were discussing CPU, we were discussing main memory. At that time, we were imagining, okay, we were assuming that we have CPU and this is directly connected to memory. This is directly connected to main memory. This is main memory. This is what we have assumed before starting the cache memory lectures. Yes or no? All the discussion was basically assuming that this CPU is directly connected to main memory. So the CPU can access the main memory, CPU can read main memory, CPU can write in main memory, CPU will generate the main memory address. That address will go on the address bus to the main memory. Okay, control signal will go on the control bus to the main memory. And then based on the control signal, whether it is read signal, write signal, based on that, either we will read from main memory or we will write in the main memory. This is what we have assumed before starting the cache memory lectures. Now, what is the problem when CPU is directly connected to main memory? What is the problem? Let me tell you the problem. Because main memory is actually very slow. Okay, it is big. That is a good thing. We want memory to be huge. Yes or no? So in our computer systems, we want huge amount of memory we want. Okay, so you can see main memory is big. That is a positive point. That is a good thing. But you can see this is slow and this is far away from processor chip. You can see this is the processor chip. If you see the hardware of your computer, you will see here, you will see there is a processor chip. Okay, here you have the CPU, and you can see this main memory is actually far away from the CPU. Okay, so because it is far away from the CPU, it is, I can say, accessing the main memory is actually very slow. Okay, so these are the disadvantages when main memory is directly connected to CPU. These are the disadvantages, that if you have to access the main memory for every access, then because main memory is slow and also it is far away from the CPU, so the access time is also more. So I can say everything will become very slow. Okay, CPU is very fast, but the main memory will become the bottleneck. The speed of main memory will become the bottleneck for the CPU. Okay, so what is the solution then? Solution is very simple. Between CPU and main memory, we can put a cache memory. Okay, and what we can do, this cache memory we will build using a technology called SRAM. SRAM. Okay, static RAM. Basically, this cache memory we will build using a technology static RAM, and this main memory we will build using the technology dynamic RAM. So this dynamic RAM technology, this is actually cheap. Okay, so we can, because it is cheap, so we can build huge amount of main memory. But because this SRAM technology, static RAM technology, that is expensive, so we will have the cache memory, but this cache memory will be smaller. Okay, it will be expensive. Cache memory will be more expensive. The static RAM technology, that is more expensive. Dynamic RAM technology, that is less expensive. So you can see this cache memory will be smaller, more expensive, but it will be very fast. Okay, and this main memory, we create this main memory, this we build this main memory using dynamic RAM technology, which is cheaper, also which is slower. So the main memory will be slower comparatively to, if you compare with cache memory, then the main memory will be comparatively very slow. Okay, and the cache memory will be very fast. So you can see between CPU and main memory we can put a cache memory, and this cache memory we will put very close to CPU. Actually, this cache memory we will put on the processor chip. Okay, on the processor chip itself we will put the cache memory. So this cache memory is very close to CPU, it is not far from CPU, like main memory is far from CPU, and this cache memory is very fast. And remember, in this cache memory we will not put the whole data. See, the complete data, the whole data you can find in the main memory, but in this cache memory, because it is smaller, so we cannot put the whole data. So what we will do, we will only put the active data in the cache memory. What is active data? Active data means the data which CPU needs currently. At this moment, the data that CPU needs, that data, that is active data, and that we will put in the cache memory. Because cache memory is smaller, if you compare with main memory, cache memory is smaller. So we cannot put the entire data of main memory in the cache memory. So we will put only the active data in the cache memory, so that CPU can, most of the time CPU will access the cache memory. And when the CPU is accessing some data and that data is not available in the cache memory, then we will go to main memory, we will bring that data in the cache memory, and then from the cache memory the data will go to CPU. Okay, so this is how we resolve the problem of connecting CPU with main memory. This, there was a problem. Okay, there were some issues. These issues we can resolve by putting a cache memory between CPU and main memory. You can see in this diagram, on the processor chip, if you zoom this processor chip, you will find that cache memory is actually on the processor chip. So cache memory is very close to the CPU. This is actually main memory, and in this processor chip, if you zoom it, you will see that the cache memory is on the processor chip. Okay, so accessing the cache memory is very fast, I can say. Accessing the main memory is very slow. Also, let me tell you that cache memory also can have levels. It can have level 1 cache, level 2 cache, level 3 cache, and so on. Okay, also the level 1 cache, okay, the level 1 cache, actually we divide this into data cache and instruction cache. Okay, so on the level 1, let me tell you that on the level 1 you can have two different cache memories. Okay, these are different physical storage, or I can say different cache memory. One is data cache, another is instruction cache. In the data cache we will put the data like operands, variables. Okay, and in the instruction cache we will put the instructions, basically the code, I can say the program, or I can say the code. So in the instruction cache we will put the instructions, in the data cache we will put the operands and variables, like this. Okay, and this level 2 cache, this is usually unified, means this is not split into data cache and instruction cache. Only level 1, this L1, I can say level 1, only this L1 cache we split into data cache and instruction cache. But the level 2, level 3, these cache memories, these are unified. Unified means, okay, we don't split them into data and instruction cache. The same cache memory, this level 2 cache, in the same cache you will have operands, data, and also the instructions. Okay, so very simple. Now let's discuss multi-level caches, or I can say cache hierarchy. As I told you that cache memory also has multiple levels. In the modern processors, we have multiple levels of the caches. We don't have only one level of cache. We don't have only one cache memory, we have multiple levels, I can say multiple levels of cache. And you can see here, this is CPU. Between CPU and main memory, we have multiple levels of cache memory: level 1, level 2, level 3. Let me tell you, the cache memory which is closer to CPU, that is called level 1. Okay, and which is far from CPU, that cache is called level 3 or level 2. So you can have multiple levels of cache memory. Okay, and here also you can see in this diagram that these cache memories, these level 1, level 2, level 3, these cache memories, they also have different sizes. You can see this L1 cache is smaller, L2 cache is bigger than this L1, and this L3 cache, this cache memory is bigger than L2. So you can see size is increasing. Okay, and also the speed is decreasing. This L1 cache will be very fast, this L2 cache also will be faster than main memory, but it will be slower than L1 cache. And this L3 cache will be faster than main memory, but it will be slower than the level 2 cache. Okay, so very simple. Okay, I hope you understood. So you can see we can have multiple levels of the cache memory. In this diagram, we have 3 levels of cache memory. You can have 2 level of cache memory, or you can have 1 level of cache memory. Okay, but usually in the modern processors, we have multiple levels of cache memory. Okay, and remember, the level of cache which is closer to CPU, that is called level 1. Okay, and you can see the size is increasing from L1 to L3, the size is increasing, and the speed is decreasing from L1 to L3. Very simple. So you can see this L2 cache memory, this is slower than L1, but it is larger than L1. The L3 cache memory is slower than L2, but it is larger than L2. Okay, very simple. You can see in this diagram also that on the processor chip, we put the L1 cache. And let me tell you, the L2, L3 cache, either you can put on the processor chip or you can put them off chip. So let me tell you, there is something called on chip. Okay, and there is something called off chip. What is the meaning of on chip? On chip means on the processor chip. On processor chip means closer to CPU. Okay, on processor chip means it is basically, I can say, closer to CPU, closest to CPU. Okay, and off chip means off the processor chip. Okay, so let me tell you that these levels of cache memory that we have, L1, L2, L3, among them, on chip is L1 cache. Okay, L1 cache, that is on chip, and this L2, L3 cache, they can be on chip or they can be off chip. Okay, this L1 cache, this is always on chip, and this L2, L3 cache, they can be on chip or they can be off chip. So you can see this L2, L3 caches, they can be either they can be on chip or they can be off chip. Okay, I hope you understood this. So you can see in this diagram, you can see that on processor chip we have L1 cache and also we have L2 cache. So in this diagram you can see we have 2 levels of cache memory, L1, L2. Here remember this L1 cache, this is called primary cache because this is closer to CPU. First we will look in the L1 cache. Whenever the CPU will generate the main memory address, remember CPU is thinking, CPU does not know about the levels of the cache memory. CPU does not know whether there is a cache memory or not. From the CPU point of view, there is a main memory. From the CPU point of view, CPU is generating the main memory address. So CPU will generate the main memory address, but with that address, first we will go to the primary cache, or I can say L1 cache. If there is a hit in the L1 cache, then from the L1 cache we can send the data to the CPU register. If there is a miss in the L1 cache, then we will go to L2 cache. If there is a miss in L2 cache, then we will go to main memory. Okay, like that. So you can see that from the CPU point of view, CPU does not know about the levels of the cache memory. CPU does not know about the cache memory also. The address generated by the CPU in context of cache memory, when we study computer architecture, when we study computer, I can say cache memory, when we study, then the last level of the last level of memory, we assume that is main memory. Okay. And remember, when we study operating system, when we study virtual memory, then we assume that last level of memory is a hard drive, or I can say hard disk. So you can see from the cache memory point of view, from computer architecture point of view, we assume that main memory is the last level of memory hierarchy. Okay, and the first level of memory hierarchy, that you can assume that is registers. But registers accessing register is very fast. Okay, I can say the access time of register is negligible. Okay, you can just consider that access time of register, that is negligible. Okay, so you can assume that in the memory hierarchy, you can assume that this L1 cache, this is the first level, but you can assume registers are the first level, but they don't have any access time, or I can say negligible access time. Then the access time will actually increase. If you want to access the main memory, that will take more time than accessing the cache memory. Okay, so you can see here multi-level caches we have seen. There is a primary cache that is called L1 cache. Remember, in the modern computers there are two or more levels of cache memory, and the cache memory which is closer to CPU, that is called L1 cache or primary cache. And this is very fast, but it is slow, but it is small. It is very fast, but it is small. Okay, and you can see then we have L2 cache, then we have L3 cache. And as I told you, this L1 cache, this is on chip, means this is on the processor chip. And this L2 L3 cache, they may or may not be on the processor chip. They can be on chip or they can be off chip. Okay, and remember, L1 cache, L2 cache, L3 cache, all the three cache memories, they are basically cache memory. So we build them using the SRAM technology, static RAM. Same technology we use for L1 cache, L2 cache, L3 cache. But remember, L1 cache is actually smaller. So checking in the L1 cache will take less time. I can say the access time of L1 cache will be very low. Okay, but you can see L3 cache actually will be large. So because L3 cache is big, it is large size, so the access time of L3 cache also will be more than the access time of L2 and L1 cache. Okay, very simple. You can see in this diagram that we have level 1 cache, L1 cache, L2 cache. Here in this diagram you can see we have total two levels of cache memory. Okay, and as I told you, remember this level 1 L1 cache, we usually divide the L1 cache into data cache and instruction cache. Okay, so let's discuss the unified versus split cache. As I told you that this L1 cache at the level 1, we in the modern processors we usually divide this L1 cache into two physically separate caches. Okay, two separate caches on the L1. One is data cache, this is called D cache. L1 data cache, in short we call it D cache. Here in this data cache we store the data means operand and variables. And you can see there is L1 instruction cache, we call it I cache, this is the short. And in this we store the program instructions, or I can say the code to be executed. Now you can imagine what we do. If the CPU wants data, then first we will go to the data cache. If CPU wants instruction, then first we will go to the instruction cache. Okay, remember we will always go to the level 1 cache, but if the CPU wants to access variable or operands, basically the data, if the CPU wants to access the data, then first we will go to data cache, L1 data cache. If the CPU wants to access the instruction, then first we will go to instruction cache. If on the level 1, if you cannot find the desired data or instruction, then you will go to level 2. And this level 2 is usually unified. Okay, so you can see here, I've written that usually the remaining levels L2, L3, these remaining levels, they are usually unified. Okay, you can see here I've written at higher levels like L2, L3, they are typically unified caches. Unified caches means they don't have separate separate caches for instruction and data. Basically they are unified caches, means they will hold data and instruction together. Okay, very simple. You can see in this diagram that usually we split the L1 cache into data cache and instruction cache. Both are at the level 1, both are L1 caches, but remember they are they are physically separate caches, I can say. If the CPU wants to access data, then it will go to data cache first. If CPU wants to access instruction, then we will go to instruction cache first. Okay, instruction cache will give instructions and the data cache will give data. Okay, very simple. Now let's come back to memory hierarchy. We have seen that memory in the computer systems, in the modern computer systems, the memory is built hierarchically in the different levels or in the different layers. You can see CPU has registers. Accessing the register is very fast, or I can say negligible access time. The registers have negligible access time. So CPU can access the registers very fast. If the data is not in the registers, then CPU will generate the memory address, With that memory address, first we will go to the cache memory. Okay, if the data is in the cache memory, then we can provide this to CPU. If the data is not in the cache memory, then we will go to main memory. If the data is not in the main memory, we will go to the disk. Okay, so you can see in the computer systems, the memory is built hierarchically. There are different levels you can see. Okay, the closer to CPU, you can see between CPU and main memory there is cache. Okay, between CPU and disk, you can see there is main memory also. So you can see that the memory in the system is built hierarchically, very simple. We don't have the whole memory in a single level. We don't have that. Okay. So in the computer system, the entire memory that we have, that is basically divided into levels, or I can say it is built hierarchically. There is a hierarchy, memory hierarchy basically. Okay. In this diagram, you can see this is the memory hierarchy. You can see closer to CPU, that is registers. They have negligible access time. Then after that, we have level 1 primary cache, or I can say L1 cache. We have L2 cache, then main memory, and then there is magnetic disk, or I can say hard drive, hard disk. You can easily see that when you go far from CPU in this memory hierarchy, let me tell you that this top level, this is called upper level, and this is called lower level. Okay, from the CPU point of view basically. Okay, always think from the CPU point of view. So from the CPU point of view, I can say these are the upper levels, like this L1 cache, this is the upper level, and this main memory, this is the lower level. Okay, so you can see when you go from upper level to lower level, when you go, then you will see that size will increase. The magnetic disk, the hard drive size is, I can say, that is much more than the main memory size. The main memory size is much more than the cache memory size. So you can see the size will increase, the memory size will increase, or I can say memory capacity will increase. But you can see speed will decrease. Okay, the magnetic disk, the hard disk is very slow. Main memory is slower than the cache memory. Okay, so you can see the speed will decrease, or I can say in the upper levels you have more speed. Okay, and also the cost will decrease. You can see the magnetic disk, the hard disk, that is very cheap. Okay, the cache memory is actually very expensive. So you can see the cost actually will decrease, size will increase, and also speed will decrease. Okay, so these are the properties of memory hierarchy. I can say the fastest memory is closer to the CPU. What we do in this memory hierarchy, we put the fastest memory closer to the CPU. Okay. Now let's see, why do we build memory hierarchy? You might be thinking, sir, why don't we have single level of memory? This is CPU, this is memory. We don't need different levels of memory. We don't need main memory, hard drive, static RAM, or I can say cache memory. We don't need different types of memory. These are different types of memory, yes or no? So you can see, you might be thinking, sir, we don't need different types of memory. Let's have a single memory. Okay, a single fast memory. Then you can see what I will ask you. If you don't want different types of memory, if you don't want different levels of memory, then what do you want? Then you will say that I want a single level of memory. This should be very fast, this should be very big, because you want a big memory also, you want a very fast memory also. Okay, and you want a very cheap memory also, yes or no? All these three properties you want. Everyone wants these three properties from the memory. Okay, we want very fast memory, very big memory, and also very cheap memory. These three properties we want. And let me tell you, if you want these three properties, then you cannot have single level of memory. You must have a hierarchy of memory. You must have different types of memory in your computer system. You cannot just have a single level of memory. What is the reason? Let me tell you. The reason is, the memory which is cheap, that is very slow. The memory which is fast, that is expensive. Okay, so you can easily see that if you want all these three properties, if you want fast also, memory should be fast also, memory should be affordable also, cheap also, and memory should be large quantity also. Then you can see these three properties, if you want to satisfy, then you cannot have single level of memory. Okay, you need to have different types of memory, and they must be divided into different levels. Okay, let me tell you why. What is the reason? Because you can see, what is the you want cheap memory, right? Okay, so if you want cheap memory, then you can see disk is very cheap. Okay, hard drive, I can say hard disk, magnetic disk, that is very cheap, but that is very slow also. Okay, so now you will say, okay, I don't want slow, because this is very slow memory. Okay, this is very slow memory. Now you say that, okay, I don't want very slow memory, so let's have something medium. Means, okay, the cost will, like this disk is actually cheapest, I can say. Disk is cheapest. Okay, let's go to cheap. So you can see the main memory, or I can say DRAM. This technology, I can say dynamic RAM technology. This is the name of the technology. Let me tell you, DRAM. This is the name of the technology, and using this technology, we create physical memory, or I can say main memory. Okay, so the main memory. Now you can see main memory is actually comparatively cheaper. Okay, remember this is not, I can say disk is cheapest. Okay, and the this DRAM, or I can say main memory, that is cheap. So you can see this is actually comparatively faster than the disk. But remember, this is slow. I can say this disk is slowest, but this is slow. Okay, if you come to cache memory, that is built from SRAM technology. Okay, cache memory, this is a fast memory, and we build it. Okay, to build this cache memory, we use the SRAM technology, static RAM technology. So you can see this is actually expensive. Okay, but remember this is fast. So you can easily see, if you want cheap also, fast also, and large size, okay, then if you want all these three properties, then you can never get them in a single level of memory. Yes or no? That is the reason you must use different types of memory, different levels of memory. Okay, so this is the complete idea. I hope you understood. So remember, what is the purpose of memory hierarchy? The purpose of memory hierarchy is to have fast memory, to have lots of memory, and to have cheap, or I can say affordable memory. So if you want all these three properties, then you cannot use a single type of memory. You cannot use a single level of memory. You must use different types of memory, SRAM technology, DRAM technology, and also the magnetic disk. So all the different types of memory you need, and different levels of memory you need, if you want all these three properties. Okay, very simple. So let me tell you here, you can see the main memory, that is built that is built using DRAM technology. So this is the name of the technology, dynamic RAM. Using this technology, we build the main memory. But remember, this is slow, and it is cheap per bit. Okay, per bit it is cheap. Because it is cheap, so we can use huge amount of main memory. Okay, but remember, it is slow. And you can see there is SRAM technology. Using that technology, we build cache memory. This is fast, cache memory is fast, but it is expensive per bit. Okay, so very simple. The main memory is slow, but it is cheap, so you can make large amount of main memory. The cache memory is fast, but it is expensive, so you will build small amount of cache memory. So we have seen that to satisfy three properties, fast memory, cheap memory, and also huge amount of memory, to satisfy all these three properties, we cannot use a single type of memory, a single level of memory. We need to use different types of memory and different levels of memory. So we need to make the memory hierarchy. Okay, so what we do, what the hardware designers will do in the modern processors, they create different levels of memory. The fast memory, means cache memory, they will put closer to the CPU. So most of the time CPU will access the cache memory, and cache memory is very fast. So most of the time CPU is thinking that I'm getting the data very fast. Okay, but remember, cache memory is, I can say, very small. So what we do, after cache memory we put the main memory, after main memory we put the hard drive. Okay, and you can see hard drive, that has huge capacity. Okay, so we can put everything in the hard drive. Okay, so you can see that what CPU is thinking. CPU, most of the time CPU will access the cache memory, because cache memory we put closer to the CPU. So first the CPU will go to the cache memory, CPU will access the cache memory. And the cache memory hit ratio, let me tell you, the hit rate, if you see, the hit rate of cache memory is actually more than 90%. So almost 90% of the time the CPU will get the data in the cache memory. And that is the reason CPU is thinking that the memory is very fast. Remember, CPU does not know that there are cache memory, there is main memory, there is hard drive. CPU does not know that there are different levels of memory. From CPU point of view, CPU has generated the memory address, and now CPU is getting the data. So you can see CPU is getting the data from the cache memory 90% of the time. So that is the reason CPU is thinking that memory is very fast. In this system, memory is very fast. But CPU does not know that this data is coming from the cache memory. 90% time, this data is coming from the cache memory, and cache memory is very fast. So that is the reason CPU is thinking that, okay, in this computer system, there is a very fast memory. Okay, and you can see cache memory is small, but remember, hard drive is very huge. Okay, so you can see if the data is not in the cache memory, then we can fetch the data from main memory to the cache, or we can fetch the data from disk to main memory, from main memory to cache. So you can see only 10% of the time, the miss rate, only 10% of the time the data will not be available in the cache memory. Okay, so for only 10% of the time we need to access the main memory, or we need to access the hard drive. So you can see CPU is thinking that in this computer system there is a huge amount of memory, and the memory is very fast. So you can see this is an illusion. Do you agree with me? We are getting the CPU is having an illusion that there is a large amount of fast memory. So let me tell you, using this memory hierarchy, a very smart this is a very smart idea. Let me tell you, this memory hierarchy is a very smart idea. Using this memory hierarchy, what we have done, we have created an illusion that there is a large amount of fast memory. CPU is having an illusion that there is a large amount of fast memory. Okay, and remember, to create this illusion, what we do, we use the hierarchical memory structure. We create multiple levels of memory. We put the fastest memory, the cache memory, we put closer to CPU, then the main memory, and then the hard drive, like that. Okay, now if you let me ask you one question now. I told you that the memory hierarchy that is successful only when CPU is getting the data from the cache memory most of the time. Do you agree with me? Otherwise, the memory hierarchy will not be successful. I am saying that memory hierarchy will be successful only if the hit rate is 90% or more than 90%. Then only the memory hierarchy will be successful. Do you agree? If most of the time data can be found in the cache memory, then only this memory hierarchy will be successful. Now, can you guarantee that for most of the programs we will have 90% hit rate in the cache memory? Can you guarantee that? How can you guarantee that? Very simple question I am asking you. What is the guarantee? Who is giving this guarantee? I am asking, what phenomena, what factor, what is something that is giving you the guarantee that for most of the programs, for majority of the programs, in the cache memory the hit rate will be 90%? Means most of the time CPU will get the data in the cache memory. Okay, CPU will find the data in the cache memory. So that is the reason CPU will have the illusion that we have huge amount of fast memory, this illusion. But remember, to have this illusion, illusion of huge amount of fast memory, to have this illusion we must have high hit rate in the cache memory. Who is giving you the guarantee that for most of the programs you will have high hit rate in the cache memory? So the answer is temporal locality and spatial locality, locality of reference, if you remember. Because remember, I told you that most of the programs, they have locality of reference. Means they have temporal locality, also spatial locality. The definition of temporal locality and spatial locality we have already seen in the first lecture of cache memory. What was temporal locality? Temporal locality means if the program will access some memory location, then in the near future there is very good chance that it will access the same memory location again. So you can see this is the definition of temporal locality. If the CPU is accessing some memory location, then in the near future there is high probability that same memory location the CPU will access again. So this is called temporal locality. And what is spatial locality? Spatial locality says that if CPU is accessing some memory location, then in the near future it is there are good chances in the near future you will access the nearby locations. So you can see this temporal locality and this spatial locality, this is the definition. And most of the programs have temporal locality and spatial locality. See what most of the programs will do. Most of the programs will spend most of the time in the loop. Yes or no? In your program, whenever you have written a program, then most of the time is consumed in the loop. There is a loop, and whenever there is a loop, then what we are doing, we are executing the same instructions again and again. So that is called temporal locality. And also, because most of the time is consumed by the loop in the entire program. Okay, if you see the entire program, then in the entire program most of the time is consumed in the loops. So in these loops, you can see in these loops all these instructions you will fetch again and again, you will execute them again and again. So this is the example of temporal locality. And also you can see that the computer, what it will do, it will execute the instructions in a sequence. Yes or no? It will execute this instruction, then this instruction. Okay, if the instruction is not a branch instruction, then most of the time, majority of the time, the CPU will execute these instructions in a sequence. This is the example of spatial locality. Means if you access a memory location, then in the near future you will access the nearby locations. Okay, so you can see most of the programs, if you notice, they have temporal locality, also spatial locality. Programs have temporal locality in the data also, temporal locality of data. Also, programs have temporal locality of instructions. So temporal locality of data access as well as temporal locality in instruction access. Also spatial locality in data access, also spatial locality in instruction access. So basically the programs have the spatial locality and temporal locality in data access as well as in the instruction access. And most of the programs have this temporal locality and spatial locality. That is the reason when the data is not available in the cache memory, then what we will do, we will fetch the entire block. See, CPU just wants one byte. CPU wants only one byte, only one location. Okay, and if this location is not available in the cache memory, this is the cache memory, then what we will do, we will fetch entire block of data. This entire block of data we will send to the cache memory. What is the reason why we are sending this entire block of data to the cache memory? CPU just wants one byte. Let's assume this is the block. CPU only wants one byte or one word, but we still what we are doing on cache miss, we are sending this entire block of data to the cache memory. What is the reason? The reason is very simple, because we know that most of the programs have temporal locality and spatial locality. And because of spatial locality, we know that if CPU wants to access this location, then in the nearby future, this CPU will access the nearby locations, yes or no? So that is the reason what we are doing. We are sending this block to the cache memory so that next time next time the CPU will access the nearby locations and it will find in the cache memory. So you can see the hit rate of cache memory is almost 90% or more than 90% because of spatial locality and temporal locality. So overall, the conclusion is this, that most of the programs have temporal locality, spatial locality. That is the reason we are getting 90% hit rate, or I can say more than 90% hit rate in the cache memory. And that is the reason CPU is thinking that I am getting the data very fast. 90% times I am getting the data very fast. Okay, so CPU is thinking, CPU is having this illusion that in the computer system, in the system, there is huge amount of fast memory. I hope you understood this complete explanation. Okay, so you can see this, the effectiveness of cache memory, or I can say the effectiveness of memory hierarchy, that is due to the property of computer programs, that is locality of reference. They can ask you in the gate exam, why cache memory is successful? What is the reason for effectiveness of cache memory? What is the reason for effectiveness of memory hierarchy? Why memory hierarchy is successful? The reason is very simple, because majority of the computer programs have this locality of reference, temporal locality and spatial locality. And that is the reason for majority of the computer programs, in the cache memory the hit rate is 90% or more than 90%. So almost 90% times the CPU will get the data from the cache memory. Cache memory is very fast, so CPU is thinking that in the system there is huge amount of fast memory. So this illusion is created by memory hierarchy, and the success of memory hierarchy depends on the locality of reference, on the temporal locality and spatial locality. I hope you understood this complete explanation. Okay, and that is the reason, remember, from the main memory, when we send data to the cache memory, then we do not send only one byte or one word. We do the block transfer. The entire block of data we will transfer to the cache memory because of spatial locality. Okay, because we know that in the nearby future the CPU will access the nearby locations. So that is the reason the entire block of data we send to the cache memory, so that in the next time when the CPU will access the nearby locations, then it will find the data in the cache memory. But remember, CPU only wants one word. So from the cache memory we will only send one word to the CPU. And typically this register size is also equal to word size. So you cannot send the block of data to the register. From the cache memory, one block of data you cannot send to CPU, because in the register, in the CPU there are registers, and the size of register is same as word size typically. So from the cache memory, in the cache memory you are getting the block from the main memory, but from the cache memory you are sending a word to the CPU register. Okay, very simple. I hope you understood this. So we have seen that memory is built hierarchically. There is a memory hierarchy in our computer systems. We don't have a single type of memory in our computer system. We don't have a single level of memory in our computer system. We use different types of memory: cache memory, main memory, hard drive. We use different types of memory, and we have different levels of memory. Okay, the fastest memory, the cache memory, we put closer to the CPU. Then after cache memory there is main memory. After main memory there is hard drive, hard disk. Okay, so basically the memory in the computer system is divided into levels, or I can say into hierarchy. There is a memory hierarchy. This is what we have seen. But remember, there is a hierarchy, there are many levels of memory, that is fine. But the transfer of data will only happen between two adjacent levels at a time. If you see, at a time, the data will be transferred, the data will be copied between two adjacent levels only. What it means? It means that when the CPU will generate the memory address, remember, CPU does not know about level 1, level 2, level 3 caches. CPU does not know about the cache memory also. The last level of the memory is main memory. One more thing, when you study operating system, when you study virtual memory, in the context of virtual memory, the last level of memory is actually the hard disk. Okay, but remember, when you study cache memory, or I can say when you study computer architecture, from the cache memory point of view, from in the context of cache memory, the last level of memory we assume that is main memory. Okay, so we assume that main memory has everything, and from this main memory, some subset we will copy to the cache memory, and from the cache memory we will send the data to the CPU. So let me tell you here, when the CPU is generating the memory address, CPU will not generate the cache memory address, because CPU does not even know about the cache memory. Is this clear? So CPU does not generate level 1 cache address, level 2 cache address. No, not like that. CPU does not generate the cache address. CPU will generate the memory address. That's it. Okay. So now when the CPU has generated the memory address, the main memory address, then first we will go to the level 1 L1 cache. If there is a hit, the data we will send to the CPU. If there is a miss, then we will go to level 2 cache. Okay, if there is a hit in the level 2 cache, then we will send the block of data to the level 1 cache, and then one word we will transfer to the CPU. So you can see, from the cache memory to the CPU we do the word transfer, and from main memory to cache memory we do the block transfer. Okay, you can also see, from level 2 cache to level 1 cache we do the block transfer, and from L1 cache to CPU we do the word transfer. Also remember, if there is a miss in the L2 cache, then we will go to L3 cache. In the L3 cache, if there is a hit, then we will transfer the block to L2 cache, then we will transfer the block to L1 cache, and then we will transfer the word to the CPU. Okay, if there is a miss in the L3 cache, then we will go to the main memory, then we will bring block of data. The block of data we will transfer to L3 cache, the block of data we will transfer to L2 cache from L3, then from L2 to L1 block of data we will transfer, and then from L1 cache to CPU we will transfer the word. Okay, so I hope you understood this point. So remember, there are different levels of memory. There are three levels of cache memory. There is main memory. Okay, there might be hard drive also. So you know that in our computer system we have different levels of memory, but at a time, the data will be copied, the data will be transferred between two adjacent levels only. Okay, it's not like from L3 you will not directly send the data to the CPU. Okay, the block of data you will transfer to L2, the block of data you will transfer to L1, and then word you will transfer to CPU. So like this. Okay, so you can see, in this diagram you can see that at a time the data will be transferred between adjacent levels only. Okay, so this is the memory hierarchy that we have seen. This is the final conclusion, that closer to CPU, in the CPU, on the processor chip, CPU has registers, and these registers are very fast. They have negligible access time. Then we have L1 cache, L2 cache, L3 cache. Cache memory we build using the SRAM technology, static RAM technology. Using this technology, we build the cache memory, and the cache memory is very fast, but it is very expensive. Okay, then we have main memory. We build this main memory using the dynamic RAM technology. Then we can have hard drive and all these things. Okay, and you can see that from the main memory we copy a block of data to L3. So you can see L3 cache will hold the block of data. Line size is equal to block size. So you can see the L3 cache will hold block of data that is retrieved from the main memory, that is fetched. Retrieved means fetched. So that is fetched from main memory. Similarly, From L3 cache also, we will send the block of data to L2 cache. So L2 cache will hold the block of data retrieved from L3 cache. Then from L2 cache to L1 cache, we will send one block of data. So L1 cache will hold block of data, or I can say cache lines retrieved from L2 cache. And then from L1 cache to register, we will send only one word. So you can see the CPU register will hold word that is retrieved from cache memory. Okay, and when you go, remember this is the upper level, these are the upper levels, these are the lower levels. So from the CPU point of view, the closer memory, that is upper level, and the far away memory, that is the lower level. So when you go down the level, then the size will increase. Okay, but remember, it will become slower and slower. So I can say size will also increase, access time will also increase, and it will become cheaper. Okay, very simple. So this is the complete explanation of memory hierarchy. I hope you understood. Let's see a note. Note number one. The lowest level, or I can say the last level of memory hierarchy, consists of main memory in the context of cache memory. So when you study cache memory, in the context of cache memory, in the context of computer architecture and computer organization, the lowest level or the last level of memory hierarchy, that is the main memory. Okay, and when you study virtual memory, in the context of virtual memory, the last level of memory hierarchy is hard drive or hard disk. Also, one more important point, as I told you, in the context of cache memory, when you study cache memory, then the lowest level, the last level of memory hierarchy, that is the main memory. So let me tell you, CPU will generate the main memory address. CPU will not generate the cache memory address. CPU will generate the main memory address, and with that address, first we will search in the cache memory. Then, if there is a cache miss, then we will go to the main memory. But remember, from the CPU point of view, there is a main memory. CPU is not aware about the cache memory, about the levels of the cache memory. From the CPU point of view, it will just generate the main memory address, because in the context of cache memory, when you study cache memory, then we assume that last level of the memory hierarchy, that is the main memory. Let's see the note number two. The processor does not know, or I can say does not need to know explicitly about the existence of the cache memory. CPU does not know about the cache memory. CPU will not generate the cache address. CPU will not generate the cache request. CPU will simply generate the main memory request. CPU will simply generate the main memory address. Okay, so you can see CPU will simply issue read and write request using the main memory addresses. Okay, CPU doesn't issue two different type of request, like okay, this is cache request, this is memory request, not like that. Okay, it will always generate, you can see it will always issue, the CPU will always issue the main memory request. And using that main memory address, first we will check in the cache memory whether there is a hit or a miss, whether that main memory address is already available in the cache memory or not. So let's see note 2 continued. So this statement, remember, from the CPU point of view, the entire memory hierarchy will appear to the CPU as a single memory unit. Okay, remember, there is a memory hierarchy, there are different levels of cache memory also. But from the CPU point of view, to the CPU, the memory in the system, the CPU is thinking that memory in the system is a single level of memory, or I can say single unit of memory. And you can see, as I told you, in the context of cache memory, the last level of memory is assumed to be main memory. So CPU is thinking that in the system there is only main memory. CPU does not know about levels of the cache memory. Okay, so that is the reason CPU will always generate the main memory address. But with that address, we will go to the L1 cache, then L2 cache, like that. Okay, only if there is a miss in all these three levels of cache memory, when there is a miss, then we will fetch the data from the main memory to L3, from L3 to L2, from L2 to L1, from L1 to CPU. Okay, I hope you understood this point. Now let's see memory read operation in the memory hierarchy. Right now we will only discuss the memory read operation, not the memory write operation. The memory write operation we will discuss when we study write policy, write back, write through. These policies we will study in the next lecture. There we will discuss the memory write operation. Right now let's discuss memory read operation, means CPU wants to read some data or some instruction, CPU wants to read from the memory. So let's see in the memory hierarchy how the memory read operation will be carried out. Let's see, there are two cases, either cache will be hit, either there will be cache hit or there will be cache miss. So you can see the processor will generate the read memory request along with the main memory address. As I told you, the CPU will generate the main memory address also. on the control signal, it will send the read signal. So you can see there is a read signal, also the main memory address. This is generated by the CPU. Okay. Now, what we will do? First, we will access the cache memory to see if the data is already there in the cache memory or not. The cache control, it will determine whether there is a cache hit or cache miss, means whether the requested word currently exists in the cache memory or not. If it is already present in the cache memory, then we will call it cache hit. Okay. And if there is a hit, then what we will do? If there is a cache hit, then we will send the requested word to the CPU directly from the cache memory. So you can see when there is a cache hit, then for the read operation, main memory is not involved. So you can read this line: the main memory is not involved when there is a cache hit for read operation. Okay, right now we are discussing only read operation. In the next lecture, we will discuss the write policy, write operation also. So you can see in this diagram that CPU is requesting some data, and first we will go to the cache memory. If there is a cache hit, if there is a hit in the cache memory, then this data we will transfer, this word we will transfer from CPU to, from cache memory to CPU register. So you can see when you read, when CPU want to read some data and there is a cache hit, then main memory is not involved. The another case is when there is a cache miss, the requested data is not in the cache memory. Then here also remember, the processor will first issue the read request and the memory address. The processor will generate the memory address. Also, it will send the read signal on the control line. Then first we will go to the cache memory to see if this data is already available in the cache memory or not. So the cache control, it will determine whether there is a cache hit or cache miss. Now, if this requested data is not in the cache memory, then there will be a cache miss. So you can see a read operation for a word that is not in the cache memory, that will be called a read miss, or I can say cache miss. Now, when there is a cache miss, then a block of words will be transferred from main memory to the cache memory. Let me tell you, when there is a miss, then cache memory will send the request to the main memory. Who will send the request to the main memory? CPU will not send the request to the main memory. When there is a cache miss, then cache memory will transfer the request to the main memory. Okay. And then a block of words will be transferred from main memory to the cache memory. We will copy a block of words from main memory to cache memory. And after that, the requested word we will transfer to the CPU. So you can see after the entire block is loaded in the cache memory, after that the particular word requested by the CPU will be forwarded to the processor. You can see in this diagram that CPU is requesting a data. First we will go to the cache memory to see whether there is a hit or a miss. If there is a miss, then this cache memory will transfer the request to the main memory. Then from the main memory, a block of data will be transferred to cache memory. After this block of data is loaded in the cache memory, then the requested word will be transferred to the CPU. Okay. So these are the steps when there is a miss. And when there is a hit, then these are the steps. Okay. So remember, when there is a hit and you are reading, the CPU wants to read some data. For the read operation, if there is a cache hit, then the main memory is not involved. But remember, for read operation, when there is a miss, then main memory is involved. Then we need to access the main memory. Okay, very simple. Let's discuss inclusion property of memory hierarchy. The name itself is telling you inclusion, or I can say subset, or I can say containment. So what is this property of memory hierarchy? This basically says that in most of the cases, but not in all cases, in most of the cases, the data contained in the lower level is superset of the data contained in the higher level. This is called inclusion property. What it means? It simply means that at any point of time, at any time, if you will see, the cache memory will hold a subset of data of main memory. Means the data that we have in the cache memory, that data is already present in the main memory, because cache memory is very small, main memory is very big. So remember, when there is a cache miss, then a subset of data, a block of data will be transferred from main memory to cache memory. So you can see at any point of time, the cache memory will hold the data which is subset of main memory data. Similarly, at any point of time, the main memory will hold the data which is subset of the data from disk. Okay, or I can say that the lower level will have superset of data of the higher level. This is called inclusion property. And it makes sense because remember, whenever there is a cache miss, then from the main memory, one block of data, a subset of data will be transferred to the cache memory. So at any point of time, if you will see the cache memory, the data that is held by the cache memory, that you can also find in the main memory. So the cache memory has subset of data of the main memory. Okay, if you go to the lowest level will have the entire data. Subset of data will be transferred to main memory, subset of data will be transferred to cache memory, and from cache memory, subset of data will be transferred to CPU register. So you can see in this memory hierarchy, you can notice that there is an inclusion property. Okay, the lower level will have superset of data of the higher level. But there is an important note here. So this is an important note here, that inclusion property by default doesn't hold among the cache levels. Okay, what it means? It simply means that if you focus on the L1 cache, L2 cache, L3 cache, if you focus on these three levels of cache memory, if you focus on the levels of cache memory, then by default the inclusion property does not hold. If you want inclusion property to hold, then you need to do something. Okay, in the next lecture we will study how to satisfy the inclusion property among the cache levels. But by default, inclusion property may not hold. What it means? It means that at any point of time, it may be possible that the data that you have in the L1 cache, that is not in the L2 cache. Means, let's assume in the L1 cache we have data A, but that data is not in L2, not in L3. It may happen. So this is what I'm saying, that by default inclusion property does not hold among the cache levels. It may be possible that at any point of time, it may be possible that data in L1, that is not a subset of data in L2. Now you might be thinking, see, very curious doubt you might be having, that when there is a L1 cache, then we transfer a block of data to L1 from L2. Yes or no? So when there is a miss in the L1 cache, then from L2, one block of data is transferred to L1. Now you might be thinking, definitely it should happen that L1, the data in L1 should be subset of data in L2. Yes or no? Are you thinking this? Tell me. See, I told you that when there is L1 miss, then a block of data will be transferred from L2 to L1. So you might be thinking that at any point of time, the data in L1 should be a subset of data in L2. Similarly, the data in L2 should be a subset of data in L3, because whenever there will be a L2 miss, then a block of data will be transferred from L3 to L2. So it should happen that the data in L2 should be a subset of data in L3 at any time. But let me tell you, in the next lecture, I will prove it, that inclusion property does not hold by default in the among the cache levels. If you want inclusion property to hold, then you can do something. Okay, then you will have to do something. But remember, by default, if you don't put extra efforts, then by default the inclusion property will not hold. Okay, is this point clear? Very simple point. So remember here that inclusion property by default does not hold among the cache levels. But remember, the inclusion property holds among the different types of memory, like cache memory, main memory, disk. Okay. Among these different types of memory, among them, the inclusion property holds. Okay, and remember, the last level of memory, that will always hold the entire data. In the last level, you can find the entire data. So this is an important note. Remember, many students, they have this misconception. So that is the reason I'm again telling you that inclusion property by default doesn't hold among the cache levels. Okay. In the next lecture, I will prove it, that by default, if you don't put extra efforts, then by default, among the levels of the cache memory, this inclusion property may not hold. Okay. If you want inclusion property to hold, then you will have to put some extra efforts. Okay. You have to do something. But by default, the inclusion property does not hold among the cache levels. Okay. This we will prove in the next lecture. Okay. Now let's study the next topic, that is average memory access time. So far we have discussed memory hierarchy. Now let's discuss average memory access time, AMAT. In short, we will call it average memory access time, AMAT. Before we discuss this average memory access time, let me tell you what are the alternative names of average memory access time. It is also called effective memory access time, EMAT. It is also called average access time, simply average access time. It is also called expected memory access time, also effective access time. So these are different names for this AMAT, or I can say average memory access time. These are the alternative names. Also, what is the definition of average memory access time? The definition is very simple, that from the CPU point of view, on average, this much time it takes when the CPU wants to access something from the memory. Very simple. So remember, this average memory access time, this is the latency, or I can say this is the access time, this is the delay, this is the time that CPU sees when CPU is accessing the memory. Okay, remember there are multiple levels of memory. There is a memory hierarchy. So sometimes there will be cache hit, sometimes there will be cache miss. Okay, most of the time data you can find in the cache memory, but sometimes you have to go to the main memory also. Cache memory access time is very low, main memory access time is very high. So you can see, when you access cache memory, you can do it very fast. When you have to access the main memory, sometimes when there is a cache miss, you have to access the main memory, then main memory access time is very high, I can say. So remember, sometimes the CPU can get data very fast from the cache memory. Sometimes it will take a lot of time because you have to copy the data from main memory to cache memory, then you have to send the data to the CPU. So you can see that overall, from the CPU point of view, this is CPU. Overall, from the CPU point of view, we just want to find what is the average memory access time. CPU does not know about the memory levels. CPU does not know about the memory hierarchy. CPU is generating the main memory address. CPU is thinking that I am accessing the main memory. But most of the time, the data will be found in the cache memory. That is the reason CPU will be thinking that most of the time data is coming very fast. Sometimes the data is coming slow. When there is a cache miss, then we have to access the main memory. So sometimes the data is coming slow, but most of the time data is coming very fast. So on average, how much latency, how much delay CPU sees when it is accessing the memory, that is called average memory access time. Is the definition clear? Average memory access time, the definition is clear. This is the access time seen by the CPU on average. Okay, is this clear? On average, this is the access time seen by the CPU when the CPU is accessing the memory. Very simple. Now we need to study some important definitions. Understand all these important definitions, and then your life will become very easy. All the gate questions based on average memory access time you will be able to solve very easily. Okay, so now let's study some important definitions. Hit rate, or this is also called hit ratio. Miss rate, it is also called miss ratio. So hit rate, miss rate, let's study. Then hit time, miss time. Then what is miss penalty definition? Then what is average memory access time formula? How to calculate average memory access time? So these definitions we need to understand. Also, there is a general note. Whenever you see this word latency, what it means? It simply means access time. So access time and latency, these two words are used interchangeably. Okay. So sometimes you will see cache memory latency. That simply means cache memory access time. These two words are used interchangeably. Okay. First, let's study cache hit and cache miss. What is hit rate? What is miss rate? So you already know what is cache hit. The data that CPU wants, if you can find in the cache memory, that is called cache hit. And if the requested data is not in the cache memory, that is called cache miss. So this is the definition of cache hit and cache miss. When you want to access data, who is you? You means CPU. When CPU want to access data and it is in the cache memory, then it is called cache hit. Otherwise, it is a cache miss. So you can see cache hit will occur if the cache contains the data that we are looking for, the data that CPU is looking for. And we want cache hit, yes or no? We want high hit rate. And you can see the definition of cache miss. Cache miss occurs if cache does not contain the requested data. We don't want cache miss. We want miss rate to be very low. Now let's see what is hit rate and miss rate. Hit rate, this is also called hit ratio. Miss rate, it is also called miss ratio. So cache hit rate, the definition is very simple. Out of all the accesses, out of all the memory accesses, how many are hit in the cache memory? That is called cache hit rate. So you can see, if the data is not found in the cache memory, that is called cache miss. So you can see the definition of hit ratio and hit rate. The fraction of memory accesses found in the cache, that is called hit ratio or hit rate. Means out of all the memory accesses, how many memory accesses are found in the cache memory. And what is miss rate? This is 1 minus hit rate. Because remember, for any memory access, either it will be found in the cache memory or it will not be found in the cache memory. So either it will be hit or it will be miss. So hit rate plus miss rate, that is equal to 1. So you can see miss rate is equal to 1 minus hit rate. And what is miss rate? This is basically out of all the memory accesses, how many are miss in the cache memory. Okay, so you can see fraction of memory accesses which are not found in the cache memory, that is called miss rate. Let's see the next definition, next concept, that is hit time, or I can say cache memory hit time. So what is this hit time? It simply means that you are accessing the cache memory. So the cache memory access time, that is called cache memory hit time. And it also includes the time to check whether there is a hit or a miss. So this is the definition of hit time. Hit time is the time to access the upper level of memory. Upper level of memory means cache memory. So hit time of cache memory, or I can say cache hit time, that simply means it is the time to access the cache memory. It also includes the time needed to determine whether there is a hit or a miss. So this is the definition. Read this. The time required to access the cache memory, including the time needed to determine whether there is a hit or a miss. Okay. So in simple words, I can say cache hit time is equal to cache memory access time. Okay. Very simple. So you can see cache memory hit time, that is basically the time seen by the CPU. How much time will be seen by the CPU when there is a hit in the cache memory? Means when the requested data is available in the cache memory, then how much time it will take for CPU to receive it. Okay, is this clear? So the time seen by the CPU when there is a cache hit, this is called cache hit time. In simple words, I can say cache hit time is equal to cache memory access time. It also includes the time needed to determine whether there is a hit or a miss. Okay, so you can see cache memory hit time, that is simply equal to cache memory access time. Very simple. Okay, from this diagram you can understand the hit time. When the CPU has requested some data, then we will go to the cache memory. First we will check in the cache memory. If there is a hit, then we will send this data to the CPU. So this is called hit time, or I can say this is basically cache memory access time, but it also includes the time to determine whether there is a cache hit or a miss. Because when we will check in the cache memory, then first we want to determine whether there is a hit or a miss. So that time also, this time to transfer this data to the CPU. In simple words, cache memory hit time is equal to cache memory access time. Let's see the definition of cache miss penalty. The name itself is telling you miss penalty means the penalty that you have to give when there is a miss. So after the detection of miss means you have already detected that there is a miss. Okay, you have already determined that there is a miss. The data is not available in the cache memory. We have determined it. Okay. Now, after that, the entire time taken, that will be called miss penalty. Basically, the name itself is telling you miss penalty means the penalty that we have to give when there is a miss, the cost of a miss, that is called miss penalty. So you can see the penalty or cost of a cache miss means after cache miss is detected, the whole time taken after that, that is called miss penalty. So I can say that this miss penalty, this is basically the additional time required when there is a cache miss. Okay. So the miss penalty is basically additional time required for an access, the additional time required for access when there is a miss. And what it includes, this miss penalty, remember, this does not include the time to check whether there is a cache hit or a miss. Okay, that is not included because this is miss penalty means once you detect there is a miss, after that, you can see after that the whole time taken, that is called miss penalty. In this diagram, you can understand that CPU has requested some data. We will check in the cache memory whether there is a hit or a miss. Now, once you find that there is a miss, after that, we have to pay the penalty. When there is a cache miss, then the entire time taken after that, that is called miss penalty. Okay. And what it includes, very simple, it will include the main memory access time. Because now what we need to do after cache miss has occurred, what we need to do? The cache will send the request to the main memory. From the main memory, we will transfer the block of data to the cache memory. After that, from the cache memory, we will transfer the word to the CPU. So let me tell you that after the detection of a miss, the entire penalty, the entire cost, this is called miss penalty. Okay, so remember, this is included in the miss penalty. So miss penalty does not include the time to check whether there is a cache hit or a miss. Okay, that time is not included in the miss penalty. The name itself is telling you miss penalty means what is the penalty when there is a miss. Okay, after detection of a miss, the entire time taken, that is called miss penalty. I hope you understood. So you can read this definition, that the miss penalty is basically the time required to fetch a block from main memory to the cache memory, including the time to access the block, to transmit this from main memory to cache memory, also to insert this in the cache memory, and then pass it to the CPU. So the entire time taken, that is called miss penalty. Is this clear? So after the detection of cache miss, the entire time taken, that is basically miss penalty. You can see in this definition, you can read that after the detection of miss means, okay, after this moment, or after this moment, the this entire time taken, this is included in the miss penalty. Okay, and what is this? You can see what is included in the miss penalty. We will we will copy the block of data from main memory to cache memory. We will store the block of data in the cache memory. From the cache memory, we will send the word to the CPU. So this entire time taken after the detection of a miss, this entire time taken, this is called miss penalty. Okay, this is the cost of a miss. How much extra you have to pay when there is a miss? How much additional time is required when there is a miss? This is called miss penalty. Is this point clear? Let me know. Let's see a note. For the last level of cache memory, or when there is a single level of cache memory, if you have only single level of cache memory, or if you have multiple level cache, then for the last level of cache memory, the miss penalty is same as main memory access time. Because remember, if you have a single level of cache memory, let's assume this is your cache memory, and let's assume you have a single level of cache memory, then when there is a miss, the CPU has generated the request. First, we are checking in the cache memory whether there is a hit or a miss. Now, once you have detected that there is a miss, after that, what is the penalty of that miss? That is basically main memory access time. Okay, yes or no? Because once you have detected that there is a cache miss, then after that, what is the additional time we need to spend? That is basically main memory access time. Yes or no? We need to access the main memory. So miss penalty for the last level of cache memory, or I can say when you have a single level of cache memory, then the miss penalty is same as main memory access time. Okay, so you can read this, that miss penalty, that is basically equal to main memory access time for the last level of cache memory. Or I can say when you have a single level cache memory, then the miss penalty is simply the main memory access time, because when there is a miss after the detection of cache miss, the penalty that you have to pay, that is basically you have to access the main memory. So the penalty that you have to pay, that is basically main memory access time. You can see this screenshot from computer architecture book by Professor Samruti Sarangi of IIT Delhi. Here also you can read this, that for the last level of cache memory, you can see, for example, if L2 is the last level of cache memory, then you can see here that the miss penalty for the last level of cache memory is equal to main memory access time. Okay, you can read this line. So very simple. I hope you understood. You can see this screenshot from the Georgia Tech University, that for the last level cache, okay, for the last level cache memory, the miss penalty is same as main memory access time. Latency means access time. Okay, and if you have a single level cache, then for the single level cache, the miss penalty is simply main memory access time. Okay, very simple. Let's see the next definition, that is miss time, cache miss time. Remember, miss time is different from miss penalty. What is this miss time? Miss time simply means the total time seen by the CPU when there is a miss. Read this. The total time seen by the CPU when there is a miss, that total time is basically called miss time. Means when the item is not in the cache memory, the CPU has requested some item, some data. When that data is not available in the cache memory, then the total delay seen by the CPU, that is called cache miss time. So what it includes? What do you think? This cache miss time, what it includes? It includes the cache lookup time. Yes or no? The cache hit time. Because when the CPU has generated some address, CPU has requested some data, then first we will go to the cache memory. We will determine whether there is a hit or a miss. So that hit time is included in the cache miss time. Also, when there is a miss, then penalty we have to pay. So miss penalty is also included in the cache miss time. So remember, the cache miss time is equal to miss penalty plus cache hit time, or I can say miss penalty plus cache memory access time. So please understand that what is a miss time? Miss time is the total time spent processing a miss, not just the miss penalty. See, miss penalty is the extra, or I can say additional cost of a miss. This we have already seen, that miss penalty basically, that is the additional time after the detection of a miss, the additional penalty that we have to pay, that is miss penalty. Yes or no? But what is miss time? This is the total time spent processing a miss. So it will also include the time taken to search in the cache memory whether there is a hit or a miss. So you can see the miss time, this includes miss penalty, also hit time. Is this point clear? Let me know. Very simple point. Think from the CPU point of view. When CPU has generated some request, now if the data is not available in the cache memory, means there will be cache miss. But once CPU has generated the request, after that, the entire time, the entire delay seen by the CPU, that is miss time. Okay, so it will include the time to check the cache memory for hit or miss. So you can see the miss time, it includes the cache memory access time, or I can say cache memory hit time. Also, because there is a miss, so we have to pay the penalty, we have to access the main memory. So you can see the miss penalty is also included. Is this clear? So miss time is basically equal to the total time seen by the processor when there is a cache miss. So miss time is equal to miss penalty plus hit time. You can see this screenshot from Berkeley. You can see that miss time is basically the total time spent processing a miss. The total time spent processing a miss, that is called miss time, not just miss penalty. Miss penalty means the penalty that you will pay after the detection of a miss. Miss penalty is the additional time after the detection of a miss, the additional time taken. That is miss penalty. But what is miss time? This is the total time seen by the processor when there is a miss. So you can think of miss time equal to miss penalty plus hit time. You can also see this screenshot, that cache miss time is overall time. This is the overall time when there is a cache miss. So cache miss time is equal to cache memory access time, means hit time, plus miss penalty. Okay, is this clear? You can see this is screenshot from Princeton University. What is hit time? What is miss time? You can understand hit time and miss time like this, that from the CPU point of view, you think, okay, let's assume there is a single level of cache memory. Now, if the data is available in the cache memory, then the time seen by the CPU, that is called hit time. And if the data is not available in the cache memory, then the entire time seen by the CPU, that is called miss time. Is this clear? So miss time is the time to access item which is not in the cache memory, and hit time, this is the time to access item which is in the cache memory. So I hope you understood this point. See, now we are going to solve this MIT question, and this question is the best question to understand, to have complete clarity about hit time, miss penalty. This MIT question will answer all your doubts. Let's read this question. This is a beautiful question I found in MIT. See this. The timing of a particular cache memory is as follows. Checking the cache takes one cycle. See this. At this moment, let's assume CPU has made a request. CPU has made a memory request. Now what we will do? First, we will go and we will check in the cache memory whether there is a hit or a miss. So we will check the cache memory. We will access the cache memory, right? So read this. checking the cache memory takes one cycle. After the CPU has made a request, after that, checking the cache memory will take one cycle. This is, I can say, this is one cycle. Checking the cache memory will take one cycle. Now, if there is a hit, read this. If there is a hit, the data is returned to the CPU at the end of the first cycle. So, at the end of this one cycle, if there is a hit, then the data will be sent to CPU. Okay, is this clear? The data will be sent to CPU when there is hit. Is this clear? Very simple. Now let's see the next line. If there is a miss, if there is a miss, you know that at this moment we will find out whether there is a hit or a miss. Do you agree? At this moment we will find out whether there is a hit or whether there is a miss. This we will find out. Okay, you can see after one cycle we will find out whether there is a hit or a miss. If there is a hit, then at this moment the data will be sent to CPU. Okay, you can see the question is saying checking the cache memory will take one cycle. So after one cycle we will find whether there is a hit or a miss. If there is a hit, then data will be returned to CPU at the end of the first cycle. If there is a miss, it will take 10 additional cycles. Read this. If there is a miss, then it will take 10 additional cycles to retrieve the word from main memory, store it in the cache memory, and return it to the CPU. This additional time, this is called miss penalty. Yes or no? So you can notice, if there is a miss, means after spending this one cycle to detect whether there is a hit or a miss, if there is a miss, at this moment we will find out whether there is a miss or hit. Okay, if there is a hit, we can send the data at this moment to the CPU. But if there is a miss, then 10 additional cycles we need to spend. 10 cycles. 10 additional cycles. These are 10 additional cycles. Yes or no? So 10 more cycles we need to spend. And in these 10 cycles, what we are going to do? In these 10 cycles, we will retrieve the word from the main memory, we will store that in the cache memory, and we will retrieve the word to the CPU. So remember, in these 10 additional cycles, we will access the main memory, we will store the data in cache memory, we will send the word to the CPU. Okay, so you can easily see this additional 10 cycles, this is called miss penalty. So you can see, if there is a miss, the data, it so remember, if there is a miss, then CPU will get the data at this moment. Yes or no? So you can see, when there is a miss, CPU gets data now. Okay, yes or no? So I can say CPU gets data at this moment. Let me write it here. So you can see CPU will get data at this moment when there is a miss. Okay, CPU gets data at this moment when there is a miss. Okay, now tell me, what is hit time, what is miss time, what is miss penalty? The entire thing is given in this MIT question. I hope you understood this. So tell me, just for now, just focus on finding the cache hit time, miss time, and miss penalty. This question will give you the complete clarity on hit time, miss time, and miss penalty. So tell me, what is the hit time? This one cycle, this is the hit time. This is the hit time. Okay, you can easily see from the CPU point of view. See, CPU is here. This is CPU. This is CPU. Okay, you can notice at this moment CPU has generated the memory request. If there is a hit, if the data is available in the cache memory, then after one cycle CPU will receive the data. So you can see, if there is a hit in the cache memory, then only it will take one cycle. This is your hit time, or I can say this is basically cache memory access time. So one cycle is the hit time. And these 10 additional cycles after the detection of a miss, remember at this moment you have found out that there is a hit or a miss. So if there is a miss, then at this moment you already know there is a miss. then this additional 10 cycles, this is the penalty of a miss. This is your miss penalty. This is the penalty we have to pay because of miss. And what is miss time? Tell me, what is miss time in this entire picture? What is miss time? Miss time means, think from the CPU point of view. From the CPU point of view, if the data is not available in the cache memory, total how much time it will take? Tell me, from the CPU point of view, CPU has generated the memory request at this moment. Now, if the data is not available in the cache memory, then total how much time it will take? That is 11 cycles. That is the miss time. So miss time is equal to 1 plus 11, 1 plus 10. So the miss time is equal to 1 plus 10, that is equal to 11 cycles. Okay, I hope this point is clear now. In this diagram, from this MIT question, the hit time, miss penalty, these concepts have they become clear, crystal clear? Let me know. You can read this question again. This is a beautiful question. Read the details again. The question is saying that the timing for a particular case are as follows. Checking the cache memory will take one cycle. After one cycle, we will find out whether there is a cache hit or a cache miss. So it will take one cycle to check the cache memory. You can see if there is a hit, then at the end of the first cycle, the CPU will get the data. So you can see if there is a hit, if the data is available in the cache memory, then at this moment, CPU will get the data. Okay. And if the data is not available in the cache memory, means if there is a miss, then 10 additional cycles we need to retrieve the word from the main memory, to store this in the cache memory, to return this to CPU. So this 10 cycles, additional cycles we need to spend to send the data to the CPU. So if the data requested by the CPU is not available in the cache memory, then total time, how much delay CPU will see? Total how much delay CPU will see? That is 1 plus 10, 11 cycles. This is called miss time. Miss time simply means that from the CPU point of view, if there is a cache miss, then total how much time CPU will see, total how much delay CPU will see, that is your miss time. So miss time is equal to hit time plus miss penalty. Okay, and this hit time, this is same as cache memory access time, because we are simply accessing the cache memory. And remember, this miss penalty, this is same as main memory access time, because after the detection of a miss, we have to pay the penalty, and that penalty is basically we have to access the main memory. Okay, so now I hope everything is clear. I hope everything is crystal clear. Now let's see what is average memory access time. The definition is very simple. From the CPU point of view, what is the access time to memory seen by the CPU? That is your average memory access time. Remember, we have memory hierarchy. There are different levels of memory, but CPU does not know. CPU does not know about the cache memory. CPU does not know about the levels of cache memory. CPU only knows that there is a main memory. So when the CPU will generate the memory request, when the CPU will generate the memory address, it will generate the memory address of main memory. But on the way, there is cache memory. There are different levels of cache memory. Yes or no? So there is L1 cache, there is L2 cache, and there is main memory here. But remember, CPU does not know about the cache memory, and CPU does not know about the memory hierarchy. This is CPU. Now, when the CPU will generate the address, CPU will generate the main memory address, then most of the time we will only access the L1 cache, because the hit rate of L1 cache, that is almost 90%, more than 90%. So most of the time the CPU will get the data very quickly. But sometimes there will be L1 miss, so we need to access the L2 cache. And if there is L2 hit, then we will send the data to L1, and then we will send the data to CPU. So I can say when there is L1 miss, then sometimes it will take more time. And when there is L1 L2 miss, then we have to access the main memory. So sometimes it will take very long time. So you can see 90% of time, or I can say more than 90% of time, the data will be found in the L1 cache. So most of the time the CPU will get the data very quickly, but sometimes it will take more time, sometimes it will take very long time. So on average, let's do it average. Okay, sometimes very fast, sometimes slow, sometimes very slow. So on average, what is the delay seen by the CPU? That is what we want to find out. Okay, maybe for some instruction you will just access the L1 cache and you can get the data very quickly. But for some instruction, for some data, for some variable, for some operand, you have to access the main memory. So it will take very long time. So we want to find on average what is the delay seen by the CPU on average. Yes or no? When the CPU has generated the memory request, then on average, what is the delay seen by the CPU? That is what we want to find out. That is called average memory access time. Is this clear? Let me know. Now tell me, if L1 cache has 100% hit rate, then what will be the average memory access time? Can anyone tell me? Assume, assume the L1 cache that has hit rate 100%. Assume hit rate is 100%. Now tell me, what will be the average memory access time? Average memory access time simply means the time seen by the CPU, the delay seen by the CPU on average. So tell me, if everything you can find in the L1 cache, if the hit rate of L1 cache is 100%, then you never have to go to L2 or main memory. So for every access, for every memory access, how much time we need to spend? We just need to spend L1 access time. Yes or no? So the answer will be the average memory access time, that will be same as L1 access time. Okay, L1 access time. That's it. Yes or no? Do you agree with me? But remember, we don't have 100% hit rate. That is the reason we have to consider the miss rate of L1. We have to consider the hit rate of L2. We have to consider the miss rate of L2. So all these factors we have to consider. We have to consider hit rate, miss rate of L1, L2. The entire data you can find in the main memory because this is the last level of the memory. So the entire data you will find in the main memory. This will always hit. The last level of memory will always hit. So this main memory has 100% hit rate because the entire data you can find in the main memory. But we have to consider the L1 and L2 hit rate, miss rate. These we have to consider. Also, we have to consider the access time for L1, access time for L2, and access time for main memory. Okay, so all these factors we need to consider and we need to find the average memory access time formula. Is this clear? I hope you understood this. So this is the definition of average memory access time, that this is the access time to memory as seen by the CPU. Or I can say average memory access time, AMAT. This is the expected time to access the main memory considering cache hit, cache miss. This is another definition. Average memory access time is basically the average time to access the memory considering the cache hit, cache miss, and the frequency of different accesses, like the frequency of read, frequency of write. Sometimes the sometimes the CPU will write, sometimes the CPU will read. Yes or no? Sometimes CPU will write in the memory, sometimes CPU will read from the memory. So we have to consider the frequency of read, frequency of write. All these things we have to consider. Then we have to find the average memory access time. This will be the time seen by the CPU to access the memory on average. Okay, I hope you understood the definition of average memory access time. So in this average memory access time, we have to consider everything. We have to consider the frequency of different accesses, how many read, how many write, memory read, memory read. Okay, we have to consider the cache memory hit rate, cache memory miss rate. All these things we have to consider. We have to consider the cache memory access time, main memory access time. All these factors we need to consider. Then we will find what is the average memory access time seen by the CPU to access the memory. Very simple. Now, first we will consider when we have a single level cache. Then after some time we will consider when we have multi after some time we will also consider when we have multi-level cache. But right now, just focus on single level cache that we have single level cache between CPU and main memory. Only one cache memory we have, one level of cache memory we have. Now let's see the average memory access time formula. First, you understand the logic. Whether there is a cache hit or there is a cache miss, in both the cases, we always have to access the cache memory. Do you agree with me? To check in the cache memory whether there is a hit or a miss, we have to access the cache memory. So you can see, you can read this. All the memory accesses will need to access the cache memory, whether there is a hit or there is a miss. It doesn't, irrespective of hit or a miss, we always have to access the cache memory to check whether there is a hit or a miss. So you can see whether there is a hit or whether there is a miss, we always have to spend the hit time, or I can say cache memory access time, we always have to spend. Then you can see, when there is miss, a fraction of accesses will be miss, they will not be found in the cache memory. So for them, we have to proceed to the main memory. Remember, all the accesses will hit in the main memory, because main memory is the last level of memory hierarchy. So all the accesses will hit in the main memory. Main memory has 100% hit rate. Okay. But remember, when there is a miss, then we have to pay the miss penalty. And that miss penalty is basically main memory access time. Okay. Very simple. When we have single level cache memory, then the miss penalty is same as main memory access time. And what is hit time? That is same as cache memory access time. So irrespective of hit or a miss, first we have to access the cache memory to check whether there is a hit or a miss. If there is a hit, then that's it. But if there is a miss, then we have to access the main memory also. So let's see the average memory access time formula. When there is a single level cache memory, CPU will make the memory request. Now, irrespective of whether there is a hit or a miss, first what you will do, you will access the cache memory. Yes or no? So we will access the cache memory to check whether there is a hit or a miss. So I can say that for every memory request, definitely we have to access the cache memory. Yes or no? So I can say that this cache hit time, or I can say cache memory access time, this is same as cache memory access time. Cache memory access time. So I can say this time we definitely have to give. This time we definitely have to spend. Okay, whether there is a hit, whether there is a miss, it doesn't matter. We have to search in the cache memory for hit or a miss. So this much time we definitely have to spend on every memory request. Now, if there is a hit at this moment we will get to know whether there is a hit or a miss. Now, if there is a hit, then here the data will go to the CPU. Okay, so CPU will get the data. So you can see, if there is a hit, then CPU gets data. CPU gets data immediately at this moment. Okay, CPU gets data at this moment, I can say. Okay, at this moment CPU will get the data. At this moment CPU will get the data. Now remember, if there is a miss, when there is a miss, here remember, all accesses, for all accesses, here remember, for all accesses we will access the cache memory. So remember, this time will be spent for all the accesses, for all the memory accesses. But remember, if there is a miss, this extra time will be spent when there is a miss. So at this moment we will find out whether there is a miss or not. So if there is a miss, then we have to pay the miss penalty. Okay, so you can see, this is miss penalty. This is miss penalty. And what is this miss penalty? When you have a single level cache memory, then when there is a miss, then you have to access the main memory. So this miss penalty, this is simply main memory access time. Okay, and you can see, at this moment the CPU will get the data when there is a miss. So you can see, here CPU gets data. Here CPU gets data when miss. I hope you understood this. Now let's convert this diagram into a formula. So the formula will be like this. The average memory access time, that will be equal to, for every access we have to search in the cache memory for hit or a miss. So this cache hit time, this we always have to spend. Yes or no? For all the accesses, when the CPU will generate the memory request, then irrespective of it will be hit, it will be miss, irrespective of that, for all the memory accesses we have to access the cache memory to check whether there is a hit or a miss. So remember, this cache hit time, or I can say this cache memory access time, we always have to spend. So I can say hit time, this we always have to spend for every access. That is the reason I can say that average memory access time will be equal to hit time, because this I will do for every access, for every memory access. Now, how much extra time, and when do we pay the extra time? Extra time we pay only when there is a cache miss. So I can say, when there is a miss means 1 minus h. What is this 1 minus h? This is the miss rate. Okay, this is the miss rate. So remember, when there is a miss, only then we will pay the extra time. Okay, so you can see, only when there is a miss at this moment, so only when there is a miss, we will spend extra time. And what is that extra time? That is your miss penalty. Yes or no? So that is your miss penalty, or you can say main memory access time. So this is the miss penalty. I hope you understood this. See, very simple formula. Average memory access time is equal to, for all the accesses, whether there is a cache hit, whether there is a cache miss, it doesn't matter. For all the accesses, we will always spend the cache memory hit time, means cache memory access time. We always have to access the cache memory for all the accesses to check whether there is a cache hit or a cache miss. Now, so the so this hit time we always have to spend for every memory access. Now, how much extra time we have to spend? The extra time we will spend only when there is a miss. Only in the case of miss, we will spend the extra time. So I can say that only when there is a miss, means miss rate multiplied by how much extra time we will spend when there is a miss. The extra time will be miss penalty, or I can say main memory access time. So this is the formula, that AMAT, when you have a single level cache memory, then this AMAT formula is equal to cache memory access time TC plus 1 minus H, that is miss rate, multiplied by main memory access time, that is TM. This is the formula. I hope you understood this. Is this clear? So this is cache memory access time, or I can say this is hit time. Hit time is same as cache memory access time. So cache memory access time plus this is the extra time, and this extra time we will spend only when there is a miss. So miss rate multiplied by miss penalty. Miss penalty is same as main memory access time. For a single level cache memory, miss penalty is same as main memory access time. Okay, so this is the, so that's it. This is your AMAT formula. I hope you understood this. So you can see this. So you can see this. The cache average memory access time, that is equal to hit time plus miss rate into miss penalty. This is the, this AMAT average memory access time. This is the access time to the memory seen by the processor. Okay. So this is the formula. Average memory access time is equal to hit time plus miss rate into miss penalty. Did you understand this formula? This formula is very easy to understand, remember, because for every memory request, whatever memory request CPU generates, we will always spend hit time. We will always check in the cache memory whether there is a hit or a miss. So we always have to access the cache memory. So that is your hit time. Now, when do we have to pay extra time? We have to pay extra time when there is a miss. So I can say miss rate multiplied by how much extra time we have to pay, that is miss penalty. So miss rate multiplied by miss penalty, this is the extra time when there is a miss. And this is the hit time. This is the time for every access. And this is the additional time only for miss. So that is the reason the formula is hit time plus miss rate into miss penalty. Some students, they write the same formula in a different way. So let's see the another way of writing average memory access time formula when there is a single level cache memory. See, the idea is very simple. Either the requested data will be in the cache memory or it will not be in the cache memory. Yes or no? If it is in the cache memory, then how much time we need to spend? If it is in the cache memory, then we only have to spend the cache memory access time, or I can say cache memory hit time. So I can say when the requested item is in the cache memory, the total access time seen by the CPU will be cache hit time, or I can say cache memory access time. And when the requested item is not in the cache memory, then what is the total time seen by the CPU? The total time seen by the CPU, that will be cache memory hit time plus miss penalty. Okay, because remember, if the requested item is not in the cache memory, then also we have to first check the cache memory. So we have to access the cache memory first. And then if there is a miss, then we will pay the miss penalty. So you can see, when the requested item is not in the cache memory, then what is the total access time seen by the CPU? That is cache memory access time plus main memory access time. Because we have single level cache memory, so cache memory miss penalty is equal to main memory access time. Yes or no? So CPU will make a memory request. Now there are two possibilities. Either this will be hit in the cache or it will be miss in the cache. Yes or no? Either it will be hit, cache hit means the item, the requested item will be found in the cache memory, or it will not be found in the cache memory. So when there is a hit, then how much total access time seen by the CPU, can you tell me? When the data is available in the cache memory, then how much delay, how much access time seen by the CPU, that will be same as cache memory access time, or I can say cache memory hit time. Yes or no? So I can say that will be same as hit time, or I can say cache memory access time. Cache access time. Okay. But if the data, if the requested item is not in the cache memory, then total how much time will be seen by the CPU? Total how much access time will be seen by the CPU? That will be equal to cache memory access time plus miss penalty. Yes or no? Because remember, because remember, even if there is a miss, then also first we have to access the cache memory to check whether there is a hit or a miss. So we have to access the cache memory, and then when there is a miss, then we have to pay the miss penalty. So you can see, when the data, when the requested item is not in the cache memory, then the total access time seen by the CPU, that will be access time of cache memory plus access time of main memory. Remember, this miss penalty, this is same as main memory access time when you have single level cache memory. Because when you have single level cache memory, then when there is a cache miss, then we have to access the main memory. So this main memory access time, this is the miss penalty. So I can say this, I can also, I can also write it main memory access time. Okay, is this clear? Now this tree diagram we can convert into a formula. So what formula we are going to get? Average memory access time is equal to, you can see, either there will be hit or there will be miss. So when there is a hit, this h means hit rate. Okay, so you can see when there will be hit, then how much time will be seen by the processor, will be seen by the CPU. So when there is a hit, then we will access the cache memory, that's it. Plus when there is a miss, means 1 minus h. What is 1 minus h? This is the miss rate. When there is a miss, then what is the total time seen by the CPU, total access time seen by the CPU? That will be equal to cache memory access time plus main memory access time. This main memory access time, this is basically your miss penalty. So finally, I can say the average memory access time formula. So finally, the average memory access time formula that we will get, that will be hit rate, cache hit rate multiplied by cache memory access time plus 1 minus hit rate, that is miss rate. This is miss rate, cache memory access time plus main memory access time. And remember, this main memory access time, this is same as miss penalty. We have already seen in the single level cache memory, this miss penalty is same as main memory access time. And this TC, cache memory access time, this is basically hit time. Okay, I hope you understood. So this is the formula for AMAT. This is another way of writing the same formula. Remember, this formula, if you simplify, again you will get the previous formula. Okay, so let me explain. Let's simplify this. This this AMAT formula we got, that when there is a hit, then we will access the cache memory. Sorry. When there is a hit, then total access time seen by the CPU, that will be TC, means cache memory access time. And when there is a miss, then total access time seen by the CPU, that will be TC plus TM. Here, this TM, this is same as capital M, means miss penalty. So this is your main memory access time, and this is your miss penalty. When you have single level cache memory, then this miss penalty is same as main memory access time. Because when there is a cache miss, then we have to pay the penalty, and the penalty is basically to access the main memory. So this main memory access time, that is basically the miss penalty. Okay, so you can see TM, that is basically same as capital M. And remember, this TC, this is basically same as cache access time, or you can say this is basically hit time. You can also call it hit time. Now let's simplify this formula. So this will become HTC plus TC plus TM minus H minus HTC minus HTM. Okay, here you can see this HTC, they will cancel out. So what you got? You got TC plus TM minus HTM. Now what you got? You got TC plus, you can take TM out and it will become 1 minus H. Do you remember? This is the same formula we have already seen. Okay, so remember these two formulas, these are basically same. But if you simplify this, you will get this formula. So you can directly use this formula. And this formula is very intuitive because remember, for every access, for every memory access, we will spend the cache memory access time. And this extra time we will spend only for cache miss. So miss rate into this is the miss penalty. Okay, so you can see the same formula. I can say that this is basically hit time. This TC, this is the cache memory access time, or I can call it hit time. So I can say hit time plus 1 minus H, this is the miss rate. This TM, this is basically the miss penalty. Okay, so all these formulas are basically same. I hope you understood this. So far we have seen two formula for AMAT. Both are same formula. If you simplify one formula, you will get another formula. Now, let me share another way to write the average memory access time formula. So let's see another way of writing AMAT, average memory access time formula, when there is a single level cache memory. See, the concept is very simple. When there is a hit, means when the requested item is in the cache memory, then the total access time seen by the CPU, that is basically cache hit time, yes or no? And when the requested item is not in the cache memory, then the total access time seen by the CPU, that we call cache miss time, yes or no? This cache miss time definition we have already seen. What was cache miss time? Cache miss time is basically hit time plus miss penalty, yes or no? Cache miss time, that is basically hit time plus miss penalty, yes or no? So remember, when the requested item is in the cache memory, then the total access time seen by the CPU, that is called cache hit time, or I can say cache memory access time, because when the requested item is in the cache memory, then we will only access the cache memory. So I can say the total access time seen by the CPU, that will be cache hit time, or I can say cache memory access time. But when the requested item is not in the cache memory, then the total access time seen by the CPU, that is called cache miss time. This is the definition of cache miss time. And we have seen what is cache miss time, that is hit time plus miss penalty. So I can write the formula like this, that average memory access time, that is equal to, either there will be hit or there will be miss for any memory access. When there is a hit, then tell me what is the total access time seen by the CPU, that is same as hit time, yes or no? Plus with plus when there is a miss, means 1 minus H, this is the miss rate, and H means hit rate. So this H, this means hit rate. Now when there is a miss, then what is the total time, total access time seen by the CPU, that is called miss time, yes or no? That is called miss time. So this is another formula for average memory access time. Is this clear? Average memory access time is equal to, when there is a hit rate multiplied by hit time, because when the data is available in the cache memory, then the total access time seen by the CPU is hit time, or I can say cache memory access time, plus when there is a miss, means if the data is not available in the cache memory, then the total access time seen by the CPU, that is called miss time. And this is the formula for average memory access time. Remember one more thing, what is this miss time? You can notice this formula is same as the previous formula. In the previous formula, this miss time we have written as hit time plus miss penalty, yes or no? So you can notice this same formula I can write like this, that H into hit time plus 1 minus H into, you already know what is miss penalty. Miss penalty is same as hit time, cache memory hit time means cache memory access time, plus miss penalty. Miss penalty means main memory access time. Okay, that's it. Okay, that's it. So you can see all these three ways of writing the average memory access time formula. All these three ways are same. Did you understand? We have written three formulas we have written. And these three formulas are basically same. You can use any of them. Please tell me, is this clear? Everything is clear, let me know. So you can see this is a screenshot from Princeton University. They have written the average memory access time formula, the effective memory access time formula, in terms of hit time and miss time. You can see when there is a hit, then the total access time seen by the CPU is hit time. And when there is a miss, then the total access time seen by the CPU, that is miss time. So you can see hit rate into hit time plus miss rate into miss time. And remember, what is this miss time? This is a hit time plus miss penalty. Okay. So this is from Princeton University. This screenshot is taken from William Stelling's book. Here you can see this is another way of writing the same formula. When there is a hit, then we will spend T1, means cache memory access time. And when there is a miss, then the total time spent, that will be cache memory access time plus main memory access time. Okay, you can see if you simplify this, you will get this formula. So this is the screenshot from William Stelling book. So for average memory access time, we have seen three different formulas, but actually they are basically same. You can simplify them and you can convert them to one another. So remember, all these three formulas, these are basically same. I hope you understood. Now let's solve a lot of questions. Let's solve this MIT question. This question we have already seen. We were using this question to understand hit time, miss penalty, all those concepts. Now let's solve this question. This question is basically saying that average memory access time is already given. Now we need to find the hit ratio. So let's see this. What is this question saying? The timing for a particular cache memory is as follows. Checking the cache memory takes one cycle. If there is a hit, the data is returned to the CPU at the end of the first cycle. If there is a miss, then it will take 10 additional cycles to retrieve the data from main memory, to store the data in the cache memory, to return the data to the CPU. If we want average memory access time of 1.4 cycles, then what is the minimum possible value of cache hit ratio? To solve this question, first let's find what is hit time, miss penalty, all these things. So let's read. Let's read this line. Checking the cache takes one cycle. If there is a hit, then data is returned to the CPU at the end of the first cycle. So you can see this is your hit time. Okay, so remember what is hit time? That is equal to one cycle. This is basically same as cache memory access time. I can say this is same as TC, means cache memory access time. Okay, now let's see what is the miss penalty. You can see if there is a miss, remember after one cycle you will get to know whether there is a hit or a miss. So after one cycle you already know there is a miss. Now after one cycle, when you know that there is a miss, so you have to pay the miss penalty. So you can see it takes 10 additional cycles to retrieve the word from main memory, to store in the cache memory, and to return to the CPU. So what is this 10? This 10 additional cycles, this is basically your miss penalty. Yes or no? The definition of miss penalty, you remember, miss penalty simply means after the detection of a miss, the whole time taken, that is your miss penalty. The penalty of a miss, basically. Once you detect there is a miss, after the detection of a miss, the penalty that we will pay, that is called miss penalty. And remember, when you have a single level cache memory, then this miss penalty is same as main memory access time. Because if you have a single level cache memory, then once you detect there is a miss, then we have to access the main memory. That is the miss penalty we will pay. So here I can say this 10 additional cycles, this is your miss penalty. The average memory access time is already given to you. Can you tell me in this question what is the miss time? Remember what is miss time? Miss time is the total access time seen by the CPU when there is a miss. When the requested item is not in the cache memory, then the total access time seen by the CPU, the total delay seen by the CPU, that is called miss time. And you already know miss time is equal to hit time plus miss penalty. So tell me, what is this hit time plus miss penalty? That is, one cycle is the hit time and miss penalty is 10 additional cycles. So I can say 11 cycles, that is the miss time. Now, average memory access time is already given to us. We can use any formula you want. To solve this question, let's use all the three different formulas if you want. Let's solve this question using different formulas that we have seen. We have already seen that average memory access time, this is equal to hit time, hit time is same as cache memory access time. So hit time plus miss rate into miss penalty. Correct? This formula we have seen. So let's use this formula to solve this question. Average memory access time is given to us, that is 1.4 cycles. So 1.4 cycles. Everything is in the terms of cycles, you can see. Hit time is also 1 cycle, miss penalty is 10 cycle. Everything, the unit of every data, that is basically cycles. Okay, so you can see 1.4 cycles is equal to what is hit time, that is 1 cycle, plus what is miss rate, I don't know, we need to find the hit rate. The question is basically asking the hit ratio. So let me assume that hit ratio is h. Okay, so what will be miss rate, that will be 1 minus h into miss penalty. What is miss penalty? This is the additional time after the detection of a miss, the additional time spent. What is miss penalty? This is the additional time spent after the detection of a miss. So the miss penalty in this question, that is 10 cycles. So here I can say, so now let's solve it. 10h is equal to 9.6. So what is the hit rate, hit ratio? That is 9.6 divided by 10, that is 0.96. Or I can say 96 percentage. If you want to convert to percentage, then you can multiply with 100. So this 0.96 you can multiply with 100, you will get percentage 96%. This is the hit rate. Okay. So that's it. The question is asking for hit rate, and that we have found, that is 96%. Remember, the same question you can solve using the different formula that we have seen. We have seen a formula, average memory access time is equal to hit rate multiplied by hit time plus miss rate multiplied by miss time. This formula also you can use if you want, because when there is a hit, then the total access time seen by the CPU is hit time, and when there is a miss, then the total access time seen by the CPU, that is miss time. So I can use this formula also. So you can see h multiplied by hit time is equal to 1 plus 1 minus h multiplied by what is miss time. What is miss time? Miss time is 1 plus 10. Yes or no? The total access time seen by the CPU when there is a miss. So this is basically 1 plus 10. This is the miss time. So finally you will get h plus 11 minus 11h. And this average memory access time, this is given to you 1.4 cycles. So what you got? You got 11 minus 10h. So you got 11 minus 10h. This is 1.4. So 10h is equal to 11 minus 1.4. That will be 9.6. And again here you will get h is equal to 96 percentage. If the question asks you in the percentage, you can say 96. If the question asks you fraction, then you can say 0.96. This will be the answer for this question. Understood? Let me know. You will feel a lot of confidence now. Let me tell you. After understanding all the previous concepts, now we are going to solve many questions. Let me tell you, you will feel a lot of confidence by the end of this lecture, because all the concepts that we have seen so far, all the definitions that we have seen so far, using them, we are going to solve a lot of questions. We are going to solve gate PYQs, standard questions. So by the end of this lecture, a lot of confidence you will feel. And without any confusion, without any confusion, you will solve all the questions. Okay. This is the answer of the previous question. Let's solve this question from MIT. Problem 2. The beta engineering team is working on design of a cache. They have decided that the cache will have a total of 1024 data words. This is the size of cache memory. But they are still thinking about other aspects of the cache architecture. Now, this is the question that we need to answer. The cache takes 2 clock cycles to determine if the memory access is a hit or a miss. And If it is a hit, then we will return the data to the CPU. If there is a miss, then the cache memory will take 20 additional clock cycles to fill the cache line and return the requested word to CPU. If the hit rate is 90%, what is the average memory access time in clock cycles? This is another beautiful question. All the details are given in this question. Read this. What are the hit time? What are the miss penalty? What are the miss time? Can you tell me everything? Let me know. See this. The cache takes 2 clock cycles. Read this line. The cache memory takes 2 clock cycles to determine if there is a memory. Read this line. The cache memory takes 2 clock cycles to determine if the memory access is a hit or a miss. And if this is a hit, then at the end of these 2 clock cycles, we will send the data to the CPU. So this is your hit time. Okay. Or I can say this is the cache memory access time. This is the hit time. And you can see after and you can see at the end of these 2 clock cycles, we will find out whether there is a hit or a miss. So at the end of these 2 clock cycles, if you determine that there is a miss, if you know that there is a miss, then 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 the cache memory will take 20 additional cycles to fill the cache line and return the requested word to the CPU. So you can see these 20 additional cycles, this is the miss penalty. After the detection of miss, the entire time taken, that is your miss penalty. You can see at the end of these 2 clock cycles, we will get to know whether there is a hit or a miss. If there is a hit, immediately at the end of these 2 clock cycles, the data will go to the CPU. But at the end of these 2 clock cycles, if we get to know that there is a miss, then additional 20 clock cycles we have to spend, and this is called miss penalty. So what is miss time here? Miss time means the total access time seen by the CPU when there is a miss. So what are the miss time? Miss time will be equal to 2 plus 20. Means when the data is not in the cache memory, then what is the total access time? What is the total delay seen by the CPU? That will be equal to 2 plus 20. Because you know miss time is equal to hit time plus miss penalty. So you can see 22 cycles. This is the miss time. And here hit rate is given to you 90%. We need to find the average memory access time. So what will be the answer? Average memory access time. That will be equal to, you can apply the formula. We have seen multiple formula for average memory access time. You can apply any of them. We know average memory access time, that is equal to hit time plus miss rate into miss penalty. We can apply this formula. Hit time is 2 clock cycles. Miss rate, that is 1 minus h. We already know hit rate is 90%. So this miss rate is basically 10%. 10% in fraction, what it means? In fraction, it will be 0.10. 10% in fraction, it will be 0.10. So this is the miss rate multiplied by miss penalty. Miss penalty is basically 20 cycles. So this is the miss penalty. So finally, the average memory access time, that will be equal to what? So either you can use this formula or you can use a different formula. We have seen average memory access time formula, that is hit rate into hit time plus miss rate into miss time. So this formula also you can apply. So you can see hit rate, that is 0.9. So this formula also you can apply. Hit rate, that is 0.9 into what is hit time, that is 2 cycles, plus what is miss rate? Miss rate is 0.1 into miss time. Miss time is miss penalty plus hit time. So what is miss time? That is basically 2 plus 20. So if you want, you can apply this formula also. So using this formula also, you can simplify this. You will get the same answer, that is 4 cycles. So you can use any average memory access time formula you can apply. This is the answer of this question, 4 cycles. Let's solve another MIT question. Problem number 4. back to back I have taken questions, standard questions from MIT. All these questions, they will improve your confidence. Just solve them. So let's solve this question. This data is actually not relevant to this part A. Let's focus on this part A. So this data is not relevant here. So let's see this part A. There is a cache memory, and the question is saying that using this cache, a particular benchmark program experiences an average memory access time of 1.3 cycles. So for a particular program, this average memory access time is given to us, that is 1.3 cycles. The access time on a cache hit, that is one cycle. See this, the access time on a cache hit, that is one cycle. This is your hit time. And the miss penalty means the additional access time. The miss penalty is 10 cycles. The definition of miss penalty is also given here, additional access time. After the detection of a miss, the additional access time, that is basically miss penalty. So you can see the miss penalty is 10 cycles. What is the hit ratio? When running the benchmark program, we need to find the hit ratio. So let's solve it. First of all, in this one cycle, this is basically your hit time. You can see the access time on a cache hit, that is one cycle. So this one cycle, this is the hit time. And miss penalty is given to us, that is 10 cycles. This is miss penalty. So let's solve it. So let's apply the AMAT formula, average memory access time formula. That will be equal to average memory access time, that is equal to hit time plus miss rate into miss penalty. So what is hit time? That is given as one cycle. The access time on a cache hit, that is one cycle. So you can see hit time is one cycle plus what is miss rate? We need to find out. This question is actually asking the hit ratio. So let's assume that hit ratio is h. So what will be miss rate? That will be 1 minus h. 1 minus h multiplied by miss penalty. Miss penalty is 10 cycles given in this question. So 10 cycles, this is the miss penalty. So finally, the average memory access time that is given to you, that is 1.3 cycles. 1.3 is equal to 1 plus 10 minus 10h. So from here 10h is equal to 11 minus 1.3. So that is basically 9.7. And here h is equal to 97%, or I can say 0.97. This is the hit rate. So this is the answer for the previous question. Let's solve this question from Patterson and Hennessy book. Calculate average memory access time. Find AMAT for a processor with 1 nano. Find AMAT for a processor with 1 nanosecond clock cycle time, a miss penalty of 20 clock cycles, a miss rate of 0.05 misses per instruction, and a cache access time, including the hit detection, and a cache memory access time, including the hit detection of 1 clock cycles. Assume that read and write miss penalties are same and ignore the write stalls. So this is a very simple question. So in this question, all the details are given to us. You can see the miss penalty is given to us, the miss penalty of 20 clock cycles. The miss rate is also given to us, miss rate per instruction. You can see per instruction the miss rate is 0.05. So basically the miss rate, average miss rate is basically 0.05. And you can see the cache memory access time, including the hit detection time, that is your 1 clock cycle. So hit time is given to you, that is 1 clock cycle, miss penalty is 20 clock cycles, and miss rate is 0.05. This is the miss rate. Now we can easily find the average memory access time. You can see the question is saying that read and write miss penalty are basically same, so you don't have to worry about it, and you can ignore all the remaining write stalls. So basically the information that is given, from that we can easily calculate the average memory access time. That will be equal to hit time plus miss rate into miss penalty. What is hit time? You can see that hit time is basically 1 clock cycle. This 1 clock cycle, this is basically the hit time. So I can say hit time 1 clock cycle plus what is miss rate, that is 0.05. This is the miss rate into miss penalty. What is miss penalty? That is 20 clock cycles. So that's it. Finally, the answer will be 1 plus. Here, what you can do, you can remove this point, you can divide by 100. So it will become 100 divided by 100. So it will become 1. So finally, it will be 2. 2 clock cycles. 2 clock cycles will be the answer. Okay. You can see the answer will be 2 clock cycles. And if they ask you the time, then you can say 2 nanosecond, because remember, here you can see the clock cycle time is given to you, that one cycle time is equal to 1 nanosecond. So the answer is 2 clock cycles. If they ask you, if you if they don't ask you in terms of clock cycles, then you can answer 2 nanosecond. Let's solve gate CS20. Let's solve this gate CS 2015 question. Assume that a certain processor, a read request takes 50 nanosecond on cache miss and 5 nanosecond on cache hit. Suppose while running a program, it was observed that 80% of the processor read request result in a cache hit, means 80% is the hit rate. The average read access time in nanosecond. First of all, in this question, can you tell me the data that is given to you? What is hit time? What is miss time? Can you find? In this question, first you find what is the data given to us. The question is saying that for a certain processor, a read request takes 50 nanosecond on a cache miss. Means remember, from the CPU point of view, the total access time on a cache miss, this is 50 nanosecond. So can you tell me this is miss penalty or this is miss time? Let me know. Is this miss penalty or is this miss time? Very simple question I'm asking you. The question is saying for a certain processor, a read request takes 50 nanosecond on a cache miss. So basically, this is the total access time on a cache miss seen by the processor. So this is basically miss time. This is not miss penalty. This is miss time. Okay, so please understand, this is not miss penalty. This is not miss penalty. This is not miss penalty. This is miss time. This is the total access time seen by the processor when there is a miss. When the requested item is not in the cache memory, then the total access time seen by the processor, that is 50 nanosecond. So this miss time is given to us. And you can see for this processor, this read request will take only 5 nanosecond on a cache hit. Means if the data is available in the cache memory, then the total time seen by the processor on a cache hit, means if the data is available in the cache memory, then the total access time seen by the processor is 5 nanosecond. This is the hit time. So in this question, the data that is given to us, that is from the CPU point of view. You can see the processor will generate the read request. Now, if the read request, if the data is available in the cache memory, then the total time seen by the processor will be 5 nanosecond. This is hit time. And if the data is not in the cache memory, then the total access time seen by the processor is 50 nanosecond. This is miss time. This is not miss penalty. So miss time and hit time, these are given to us. Now, hit rate is given to us, that is 80%. Now we can very easily find the average memory access time. We have already seen different formulas for we have already seen average memory access time formulas. We have already seen all the average memory access time formulas. All these are basically same formula. You can convert one formula to another. If miss penalty is given to you, you can apply this formula. If miss time is given to you, then you can apply this formula. So let's apply this formula, because in this question, hit time and miss time are given to us. So what will be the answer? The average memory access time, that will be equal to hit rate into hit time plus miss rate into miss time. Yes or no? So hit rate, that means 0.8. This is the hit rate. So hit rate into hit time. Hit time is equal to 5 nanosecond plus miss rate, that is zero point 0.2. This is the miss rate. Miss rate into miss time. Miss time is 50 nanosecond. Now we can calculate and we can get the answer. So this will become, now we can calculate and we can get the answer. This will become 4 plus this will become 10. So the final answer will be 14 nanosecond. This will be the average memory access time. Very simple. Let's solve this question from Berkeley University. Now consider that your system has 5 nanosecond of latency. Latency means access time when accessing cache memory. So the cache memory access time is given to us, that is 5 nanosecond. You can see your system has 5 nanosecond of latency when accessing the cache memory. So the cache memory access time is given to us, that is 5 nanosecond. And 70 nanosecond when accessing the main memory. So the main memory access time is given to us, that is 70 nanosecond. What should be your application's average hit rate in order to have average memory access latency? Latency means access time. So the average memory access time is given to us, that is 15 nanosecond, and we need to find what is the hit rate. So this hit rate, let me assume this is h. You can just apply the formula of average memory access time. So let's apply the average memory access time formula. What is that? So to solve this question, we can apply the average memory access time formula. We have seen multiple formula for AMAT, for average memory access time, and all these formulas are basically same. You can convert one formula to another. All are same. You can apply any of them. Okay. So let's apply this average memory access time formula, that whatever you do, we will always access the main. So let's apply the average memory access time formula that we have seen. You know that whatever we do, sorry. So let's apply the average memory access time formula that we have seen. Irrespective of hit or miss, for every memory request, we will always check the cache memory. So we will always access the cache memory. So you can see the cache memory access time, this we always have to spend. But remember, when there is miss, only when there is miss, then we have to pay the miss penalty. And when you have single level cache memory, then miss penalty is same as main memory access time. In this question, cache memory access time, main memory access time, these are given to us, and you can see the average memory access time, that is 15 nanosecond, and cache memory access time, that is 5 nanosecond, plus hit rate we have to find. This is actually miss rate. When there is miss, then we have to pay the miss penalty. This is basically your miss penalty. When you have single level cache memory, then miss penalty is same as main memory access time. The main memory access time in this question, that is 70. So now you can easily solve it and you can calculate what will be the value of h. So let's find what will be the value of h. 10 is equal to 70 minus 70h. So 70h is equal to 60. H is equal to 60 divided by 70. If you want to calculate in percentage, you can multiply with 100. If you want to calculate in percentage, then 60 by 70 multiplied by 100, that will be your answer. If you want to calculate in fraction, then this is your answer, 60 divided by 70. You can calculate. This is the answer given here. You can notice the answer will be 60 divided by 70, that we have already seen. Let's solve this question from the MIT. Assume that, let's solve this question from MIT. Assume that checking the cache on each read takes 1 cycle. Checking the cache memory for any read request will take 1 cycle, and that refilling the cache on a miss will take additional 8 cycles. When there is a cache memory, when there is a cache miss, then additional 8 cycles it will take. If we wanted average memory access time over many reads to be 1.1 cycle, this is the average memory access time we want. What is the minimum hit ratio of the cache memory to achieve this? So we need to find what is the hit ratio. Let's assume that this is h. Average memory access time that is given to you, that is average memory access time is 1.1 cycle. You can see checking the cache memory on every read will take 1 cycle. This is basically hit time, or I can say cache memory access time. This is the hit time. You can see when there is a cache miss, then additional 8 cycles we need to spend. This is your miss penalty. So we can easily solve this question. So we can just apply the average memory access time formula and we can solve this question. AMAT, that is equal to hit time plus miss rate into miss penalty. Hit time, that is 1 cycle, plus miss rate, that is 1 minus h, into miss penalty, that is 8 cycles. Already this AMAT, this is given to us, that is 1.1. So from here you can calculate what will be the value of h. You can see the hit rate that you will get, that will be this. You can see this is the hit rate that you will get, 79 divided by 80. This is the hit rate. Let's solve this GATE CS 2022 question, the latest question. Let's solve this GATE CS 2022 question. A cache memory that has hit rate of 0.8 has access latency 10 nanosecond. So the cache memory access time, latency means access time. So cache memory access time, that is 10 nanosecond. And the miss penalty is 100 nanosecond. An optimization is done on the cache memory to reduce the miss rate. However, the optimization results, this optimization will result in increase of cache access latency. We have done some optimization to reduce the miss rate, but because of this optimization, the cache memory access time, latency means access time, the cache memory access time has increased to 15 nanosecond. You can see before optimization, the cache memory access time was 10 nanosecond. After this optimization we have done to reduce the miss rate, but because of this optimization, the cache memory access time has become 15 nanosecond. Whereas the miss penalty is not affected. The miss penalty before and the miss penalty now, these are basically same. The minimum hit rate, this we need to find. The minimum hit rate, let me assume that is h. The minimum hit rate needed after the optimization, so that it should not increase the average memory access time. Means the new average memory access time should be less than equal to the old average memory access time. It should not happen that average memory access time is increasing. Okay, so let's solve it. So let's solve it. Everything is given in this question. Before optimization, after optimization. Before optimization, miss penalty is 100 nanosecond. After optimization also miss penalty is 100 nanosecond. Before optimization, cache memory access time 10 nanosecond. After optimization, cache memory access time 15 nanosecond. So you can basically create two equations: before optimization, after optimization. So you can, so you can create two equations: before optimization, after optimization. Before optimization, what is average memory access time? The formula of average memory access time we already know, that is equal to hit time, or I can say cache memory access time plus miss rate into miss penalty. So here, what is the hit time here? Hit time means cache memory access time. So before optimization, cache memory access time is 10 nanosecond. 10 nanosecond plus what is the miss rate? You can see that before optimization, the hit rate is 0.8, so miss rate is 0.2. So 0.2, this is the miss rate into miss penalty. Before optimization, the miss penalty is 100 nanosecond. So this is the average memory access time. Okay, this is basically before optimization. And after optimization, what will be the average memory access time? That will be equal to cache memory access time. After optimization, cache memory access time is 15 nanosecond plus the miss rate. We don't know the miss rate. The miss rate is 1 minus h. We are assuming that The question is asking minimum hit rate after the optimization, that let's assume that is h. So I can say after optimization the miss rate will be 1 minus h into miss penalty. Miss penalty is same, miss penalty is not affected, so the after optimization the miss penalty is 100 nanosecond. Now the question is saying that this before optimization and now the question is saying that this average memory access time before optimization and this after optimization. The question is saying that after optimization, the average memory access time should not increase. What it means? This is given in this question that this average memory access time after optimization, this is actually less than equal to average memory access time before optimization. This information is given in the question. Okay. So this equation is less than equal to this equation that is given. So I can say 15 plus 1 minus h into 100. This is less than equal to 10 plus 0.2 into 100. Now, now we can solve it and we can get the value of h. So it will be 15 plus 100 minus 100h less than equal to 100 plus this will become 20. 20. So So 100, these are cancelled, minus 100h, that is less than equal to 5. Wait a minute. Did we make some mistake? Oh, okay. ठीक. Got it. This is 10. Okay. Now let's solve it and get the value of h. So we will get 15 plus 100. 100 minus 100h is less than equal to 10 plus 20. Let's take 100h on the other side. Let's take 100h on the other side. So I can say 100h, that is basically greater than equal to, and this value we can take on this side. So 100 minus 30, that is 70 plus 15, that is 85. So I can say h is greater than equal to 85 divided by 100. Okay, so remember the new heat rate after the optimization, the new heat rate should be greater than equal to 85%. Okay, and the question is asking, so after optimization, this new hit rate, this should be greater than equal to 85%. And the question is asking minimum hit rate. So remember, the hit rate should be greater than equal to 85%. So what is the minimum value? If they ask you the minimum hit rate, that should be equal to 85%, or I can say 0.85. Here you can see the question is not asking in the percentage. The question is asking rounded off to two decimal places. So you should answer 0.85 should be the answer. Okay, that's it. So that's enough for this lecture. In the next lecture, we will discuss when we have multi-level cases, then what will be the average access. So this is enough for this lecture. I hope you understood all the concepts, all the definitions, and with confidence you can answer any question. In the next lecture, we will continue our discussion and we will find the average memory access time formula when we have multi-level cases, and some other concepts also we will study, and some more gate PYQs also we will solve. Okay. Thank you everyone. Please share your feedback. Please put a comment below. Sorry. Please like this session and please put a comment. Please share your feedback. Okay. Thank you everyone.